All right, all right, all right. My name is Tyler Sparks. I'm the lead level producer here with Ascendant Studios, and I'll be moderating this fine panel today. Before we get started, though, a couple of housekeeping things. One, there is a microphone in the middle. I don't know if you saw it when you were coming in, but that's when we're going to do our Q&A. So we're going to save time at the end here for about 10 minutes of questions, and I'll let you know throughout the talk when to get those ready. So before we get started, I'd like to introduce the panel, have them talk a little bit about their history and what brought them to Ascendant Studios. So Daniel.
Hello, everyone. My name is Daniel Chuang. I'm a lead engineer at Ascendant Studios. Started my career in games about 20 years ago on the PlayStation 2, and since done the gamut from VR to web to mobile. As for Ascendant, I remember it was about 3 years ago, at the height of the pandemic, sheltering at home with a newborn baby, and talking to Mark, Brett, and some other folks at Ascendant about this project. And I remember asking them one particular question. So these Magni in the world of Avium, are they like scholar sages or like Jedi Knights? And the short answer was battle mages. And that sold me. A little bit more to it than that, but at the end of the day, I was really excited to come in and build out something really interesting and really new and unique.
Cool, thank you, Daniel. Julia?
Hello, my name is Julia Lichtblau. I'm an associate art director at Ascendant Studios. And before Ascendant, I spent many years at Telltale Games working on some really amazing licensed IPs, Walking Dead, Batman, Game of Thrones, Tales from the Borderlands, just a lot of really amazing stylized games with a really, really strong narrative focus. And so when Brett came to me with his 60-page design doc, it read to me like a fantasy book. And I was really excited about the idea of building out a brand new world, a new IP that I would have some opportunities to create and involve, add my own ideas to, and also just be a part of a AAA experience that was so narratively focused.
Fantastic. Jason.
Hi, I'm Jason Warnke, lead combat designer at Ascendant Studios. Similarly, I've been in the industry for about 20 years as well. I used to work at Zynga, and then I moved on to licensed titles up in Seattle at Amaze Entertainment. And finally, I was working on Call of Duty with Brett. And when Brett left Call of Duty, he wanted to have this nice conversation about a game that was a magic shooter that didn't use guns, and that novelty as a designer was really interesting. How do you make a shooter without guns? And so I was really compelled, and here we are.
And last but certainly not least, Mark.
Hi, Mark Maratea. I run the engineering for Ascendant Studios. Been around the industry for a couple decades, popped through mobile, AAA. Had the fortune of doing a few new IPs, so this was not my first rodeo in Unreal with a new IP. Talked with Brett early on, and by that time, Julia had gotten together a fairly decent little sizzle pitch. Saw it about 30 seconds in and went, that looks like Hexen, but next gen, I'm in, done. Which probably dates me as a gamer of a certain age, but that was all it took for me to jump in with both feet and never leave.
Great. Well, thank you guys for introducing yourselves. Talk briefly about what this panel will be covering. We'll go through the history of the studio pretty quickly, and then focus more on how we got started on UE4, and then move to UE5. And the bulk of this discussion will be really focusing on the top advantages and disadvantages of UE5, all the trials, tribulations, triumphs that we went through as early adopters. Then we'll touch on the future of Ascendant and the Immortals franchise and get into some Q&A. So on that note, Julia, I've only been here for a few years, but you're employee number 7? Mm-hmm. Can you walk us through the history of the studio?
Sure. So, yeah, like you said, I came on as employee number 7, but the idea for the studio really started years before that, where Brett, our CEO and creative director, was working at Sledgehammer, and he always described this daydream where he was working on a level with a standard helicopter coming in and bombing and all the troops advancing down a city street. And he got to thinking, how cool would it be if instead of a helicopter, there was a dragon? And if instead of just normal soldiers, there were these battle mages who, instead of firing bullets, were flinging spells. And the more he thought of this idea, the more he looked around the landscape out there of games and was like, this seems like a really cool game. Like, why does this game not exist? I would like to build this game. I would like to play this game. So I would like to build this game. And that is really what galvanized the start of Ascendant. That's what he founded Ascendant to do, is build Immortals of Avium. And so he kind of collected a whole bunch of us from Telltale. Like Dave Bogan was employee number 6. He was ahead of me and told me how excited he was about the pitch. And so we all got together in this converted boat garage, the big roll-up doors in Sausalito, and kind of put together sort of the first inklings of this game. And gradually we moved out of that space and have just added more and more to the team, moved into a bigger office, and sort of built Ascendant into what it is today, and built Immortals into what it is today.
I love that story, going from a literal garage to like 120 employees. It's pretty cool. Cool, so thank you for that, Julia. Mark, was there ever any discussion about an engine besides Unreal? How did we get into Unreal 4?
So as Julia said, it is a small team startup with a singular vision of Brett's pitch. And so because of that vision, we already knew where the visual target was going to be, which was going to be up here. And it wasn't a what game are we making, or we're going to make a shooter and then we'll figure out, the stakes were going to be high from the get-go. And so you look at the landscape, as many of you have, of what is available to an independent studio, and that number of engines kind of collapses rather quickly. And then when you start with what's a 10-person studio going to use, the number of engines collapses to Unreal.
Right.
You need an editor. You need something that can efficiently be used. And so our studio started in August of 2018. And so we were on a vanilla 4.20. The studio quickly moved on to a source 4.21. We did a lot of work. We skipped 4.22 for reasons. We then invested heavily in 4.23. That's when we started doing a lot of systems work. By 4.25, we had, I think, run towards the limits of where Unreal 4 was taking us. We had already moved on. We had done our first vertical slice. We were working on our second, which turned into being what is our Ruins level. It's our third level in the game. For those of you that have seen some of the clips, it's got that huge battle scene where he opens the door up and the entire universe explodes behind you, which has absolutely no VFX load at all and was not troubling at all to try to get that to run performantly. So we're in Unreal 4 having built this monster, and even that, as you can imagine, for those of you who have started in 4, you come through this area, you load in your giant amount of submaps, you cripple your speed, you pause the game for a second while it has to do all the loading and unloading. And then as we get into even further, we made some interesting artistic choices throughout that level. My favorite one that I still like to poke the artists over is, for artistic reasons, we had to go through a level and we wanted the sun in a certain way to light the level in a certain way. But then you came out of that level and they wanted the sun to light the level in a certain way in a different spot. And so like any artist, they decided to put 2 suns in the world and 2 sets of big lights, and told engineering to figure out how to make that happen. And so we did, and completed that demo. And that was painful. And then they said that sounded fun and we should do that on more levels. And that sounded even more painful. And it just happens to be that was May of 21. And for those of you who know your history of Unreal, May of 21 was when Unreal 5 went into preview. So the engineering team, hearing all of those crazy art demands, and while that's going on in this concrete, built-out, polished level, we've got long talks about all these other giant levels that are being made. Brett's vision of a battle mech towering around with islands in the distance, grabbing things. We have areas where we're going to be fighting indoors and outdoors and indoors and outdoors. That's all tough to do. And so engineering team decided to grab Unreal 5 and retreat into a cave. And July 4th weekend, we pushed it into Perforce without telling anybody. And everybody came back from the holiday, and all of a sudden, we had a splash screen that said Unreal 5 and a little message in Slack saying, "Welcome to Unreal 5, good luck." And so that began our transition. We were on the cutting edge on preview. We took 5 release as soon as it came out. For reasons that, again, boil down to visual fidelity, we ended up having to take 5.1. It was slightly controversial within the studio, but at the end of the day, the biggest thing that we needed was WPO for our landscapes in order for the game to meet the visual target that we had set. And 5.0 was not going to achieve that. So yeah, 6 months before ship, we decided to do an engine update, which probably will make some of you squirm in your seats, because that was a lot of fun.
Lots of fun. OK, so thank you for getting us into Unreal 5. Looking at it from the art perspective, Julia, what were some aspects of UE5 that really dramatically improved the art team's quality of life?
Well, I think Mark definitely touched on some of it, where Lumen was just huge. It was a huge boon to us because we have such a variety of levels where, yeah, some of them are taking place on a giant mech, and some of them we are in a crazy fantasy world where there are 2 suns in the sky, because we're allowed to make that sort of stuff up. So we can have a perpetual sunset. It will be very much in both directions that you're looking. And tons of like going indoors and outdoors. And so Lumen was just amazing. Like I said, we had a really small team. We only had 4 lighters who just lit our entire game with multiple revisits to levels that you had been before that went through an entire lighting change. And so that was just like really helpful for us to move rapidly and create content and revisit that content. Similarly, you know, Nanite, I think, was the main reason that we kept poking Mark to switch over to UE5. I know Bogan and I did that quite a bit because we're so excited about just the fidelity that you're able to get out of these assets. You know, and it also worked in tandem with Lumen, because now that we're not having to worry about normal maps, you know, that tend to fall apart when you get to a certain angle or obviously get up really close to them, you know, we could create all of these assets, like there are these Tifoni rocks with all these pock marks and such, and we could just model that in. And really get this amazing fidelity and allow the player to get up right close to it, but also not have to worry about setting LODs. Like, so much of this stuff was just handled for us in the back end by Unreal, and it made the entire levels more performant when we just turned everything to nanite, including foliage, which was crazy.
Right, were there any like negatives or disadvantages to those?
Well, we certainly had to just rethink how we created content, certainly for nanite. You know, how do you go about actually unwrapping a multi-million poly asset that crashes Maya or Max when you try and import it?
Right.
And you know, we certainly, at the beginning, we just decided to add as many polys as possible because that's what Unreal could theoretically do. But at a certain point, we had to really adjust those expectations and realize that just because you can do multi-million poly assets, you don't have to. You probably should not. Right. You should probably reserve the details like for the silhouette, but you know, flat surface don't need that. And luckily, there were a lot of tools within Unreal where we could still import that giant asset, but then adjust the ratios on the fly, and that was just entirely non-destructive. And so we were like kind of pushing and pulling. Like sometimes we would overly crunch down assets, and then Bogan and I would be like, oh, that's way too far. Like, let's bring them back up and see where we can have some savings in other capacities. So we were all just constantly learning. It felt like every couple weeks we would read something on UDN or just see someone's blog post about how they were using these art tools, and we were be like, oh, let's try that, and then we developed some of kind of our own and stumbled on these things. So it was a great learning experience, and it's amazing how far we've come.
No kidding. Honestly, it's been amazing to watch. Oh. Forgive me, sorry. Jason, so talking about design, I know that world partition and data layers were a huge advantage in UE5. Can you give us some examples of the advantages and disadvantages there?
Yeah, for the level art team, the level design team, world partition was quintessential for us to be able to build these huge levels together. You know, usually when you build a level, you know, in Radiant or Unreal 4, you make a map and then you make a bunch of submaps, and let's say you have like a large level, so you have each section built into a set of submaps, like the design submap, the lighting submap, and all that, so people can work together because you're checking out a whole map to do some stuff. World partition and one file per actor meant that you're able to just put 12 people into a level and just do stuff, which was really relieving. We could all get in and start working and building together. Also, the way that we managed our organization, we had data layers, which was just phenomenal. We not only were able to tie our data layers into organization, we also were able to use that for progression. So we had a progression system that allowed us, that we tied into the data layer system that allowed us to change parts of the level depending on where you were in the game, which is really cool. Yeah.
It was great. The data layer system built into the engine to load and unload sets of actors. It was easy to add actors in and out of them. And like Jason was saying, it was a good spot for us to do our own little bit of insertion. Like Jason was saying, we tied our game's progression and eventing system to it. And so as the player progressed through the game and designers said, well, this data layer needs to be loaded in between these ranges or these ranges, it would just load in or unload as the game progressed. And Unreal did the heavy lifting. We just added that little bit to tie it into our game. And like Julia was saying, we have levels where the player comes back and revisits multiple times throughout the game, and it's slightly different. Lighting's different, the environment is a little bit different. You have all this stuff mashed together in the same space, and again, with data layers and the ease of use with them, you can adjust them on the fly or adjust them during production. And again, as the player's going through, the right sets would be loaded in based on where the player was. And again, the engine's doing the heavy lifting. We could make a little editor utility widget that says, well, I'm in the editor now. I just see everything mashed together, overlapping each other. Little utility widget that says, okay, well, I know that I have the data layers. Tell me what progression you want to use. Chapter 20, okay. And it turns off all the data layers that are not present for chapter 20. And again, little things that we can do on top of what the engine is doing the heavy lifting for us.
And also for scripting perspective, we did all of our scripting in a system we called the DLDA system, Dynamic Load and Dynamic Action, Dynamic Listener System, which was basically each actor had a set of listeners and actions that it could do. In the old, in Unreal 4, like you'd have to manage what actors are loaded and manage what is available for you to actually hook up this way. But because of the world partition system, everything was there all the time, and you didn't have to worry about things being loaded to then do listeners and actors because it was all being handled, which had its advantages and disadvantages.
Yeah. It's DLDA was a key part of our effort to not have to do so much in level blueprints or blueprints.
Or none at all.
Yeah, none at all. They turn, I think a lot of you will know, they get a little crazy. They can get a little bit crazy. So putting as much stuff into our systems, as much stuff that, they still need direction. There's still a lot of work. Designers still have to set up a lot of things, but try to take the minutia and take the micromanaging out of it. And world partition kind of lends itself to that as well. You have the system that's segmenting the world for you and handling the loading. But part of that is, well, it's doing things for you based on certain rules, and when everything's working right, it's perfect. When it's doing things that you don't want to do, then you gotta go and figure out, okay, what are the new rules here? We're not explicitly controlling loading and unloading anymore. So that was part of our learning process, is like, wait, hold on, what's going on? Why are all this stuff loaded? It shouldn't be. And going through and figuring that out.
I think that was one of our big transitions from world composition to world partition that really got us, was that moment of, I know what's loaded or not, I can have a hard reference to it, that became, I don't know what's loaded or not, I just know that nanite will at some point probably load that cell, and it may or may not load at the time I need it. And depending on what angle the player is on the player path, it may or may not be there when I send a message to it, which began the process which brought us to DLDA. So for those of you who haven't really dug in on world partition and have begun to live in this world, engineers probably speak asynchronous loading a little bit better than other departments. It's a mentality shift. The traditional version of, oh, I have a trigger and I want it to do stuff, so I drag that into my level blueprint and then I tie off a pin and I have that spawn this other thing and there's two hard references and that all works. That works really well until one of those isn't loaded and it decides to blow up. And when you're doing this in small scale, it's not such a big deal. And when your game works on happy path, it's wonderful. And then you have a player who decides to jump on top of a building and then transition through the game in a not quite happy path manner, and your game starts crashing, you get bad reviews.
Yeah, I have an example of that world partition where, or something using world partition and something that worked fine when the project was small and you have small levels that aren't very complicated. Part of this effort to take the micromanaging out of the responsibility of designers, we made an actor that handled teleports. Designers select, say, target destination, and when the right things happen, teleports the player over there. All right, why in the world is all that stuff over there being loaded there? Oh, turns out we had a hard reference between these two, between the teleport actor and the destination halfway across the map. And again, we're not careful. A lot of things that, hey, it worked. It worked, for a small project at the beginning of the project. You create these giant networks between actors that now world partition thinks, I better keep you all loaded in at the same time because you have hard references. And so a lot of our work later on, there's this broader theme of just kind of untangling and decoupling things. A lot of that, and like Mark was saying, with a lot of stuff being handled automatically, you don't have direct control over it. You're not explicitly telling it, load, unload. You still have a lot of that with, like I said, with the data layers and when we're doing certain things, but it's a big old map. You have a lot of actors interacting with each other, and you no longer have direct control over exactly when they're loading. We don't want designers to have to think about it. Engineers don't want to have to think about it, but we need to make our systems work for that. So a lot of the systems that we had before, well, that we still have, and the reason we still have them is we had to decouple that. We had to decouple where they could count on being loaded at particular times or being loaded at the same time. You can't guarantee that anymore. They may come in different orders, or they may not be in the world at all. That's just not something that you will have direct control over, and you just account for that variability.
All right, yep, okay, we're working. So on that note of like hard references and stuff, Mark, I think something everybody's curious about and we certainly have been wrestling with the entire time is memory management.
Yep. So this goes in the bucket of things I wish I knew 5 years ago. At the end of the day, when you try to ship a game, for those of you who have not gotten to this hurdle yet, Sony and Microsoft really want you to do intelligent delivery and PlayGo, and those have repercussions on how your data gets loaded. Your content folks like to start the editor in the morning, and that has repercussions on your load times. And a lot of what we discovered is, hypothetically, if you had a design team that decided to have a data table for loot, and they wanted to have specific loot lines for every different AI in your game, and so they put a hard reference to every AI in your game in that data table, and then they reference that data table in, I don't know, game instance or game mode, and then you boot the editor, it loads every single asset in your game on editor start. So things that may have bothered us, getting ready for PlayGo helped expose a lot of that. In some ways, that rigor it's the kind of thing that, again, looking back on it, I wish we had thought about early in development and had started building for PlayGo day one, well, probably day 5. But early enough that we could have taken all the benefits of ensuring pack 0 is small enough, ensuring that you can get to the main menu without overly having to load assets. It would have kept our editor load times down. It would have allowed us to have our cook times down. I know there's a lot of people who've been in the other talks. There's a lot of talks about making sure your hard references are now soft, doing untracked on some of your data tables, trying to understand how to break those reference chains. We would have individual assets that if you went in and did the reference chain check, it'd be like 48 gigs on disk, which is a little bit absurd.
Yeah,
and
data just reminding me of the wonders and horrors of the game playability system. Gas is phenomenal. It got us our whole combat system stood up really quickly, and we took a JSON-backed data table approach, which was great at the beginning because everyone could get into data tables and start messing with stuff. And as soon as someone would load up the editor without importing their JSON, they would just nuke everyone else's JSON. And then it was a nightmare, so thankfully Mark and the build team built out a build data table step in the process, so UGS would just update that for everybody and you would have less stomping. But even still, some of our data tables were JSON backed and some of them weren't, and that was also a nightmare. And then getting back to Mark's point, we had a lot of hard references, which was great for development quickly, get the FTPs and the actors who were required for certain abilities, all listed there, but then as soon as you load up a BP player character, and then every single enemy in the entire game is loaded on the main menu because they were loaded through this game playability system, we had to fix that.
Yeah, quickly. So that obviously references is a huge part. Not pulling in the kitchen sink when you're trying to do a load on stuff was huge. For those of you getting closer to finaling, memory management in general is going to be a big deal. We did a couple things for both performance reasons, because weirdly enough, the software Lumen, it runs faster than hardware Lumen. It has a second side effect of it takes about a gig less in memory because Lumen has some giant buffers. Consoles being memory restricted, that was huge. A secondary fallback from that is if you're not running hardware ray tracing, you don't need nanite mesh, the fallback meshes. So again, depending on your game and how heavy your nanite is, as I stare heavily at Julia's team, that can net you savings. For us, I think that ended up being about 2.7 gigs at runtime in our heaviest levels, which on a 16 gig console is quite substantial. That actually leads into another huge discussion that Julia had talked about, which is playing with the mesh keep percentages and understanding that, but also understanding there's a difference between the thing you export from Maya and how Nanite does the micropixelization of that and what it comes out with. And if you're not paying attention to the numbers on both ends of that, you can get in a really bad place where your fairly reasonable Maya object becomes a completely unreasonable 90 million poly Unreal object because Nanite goes nuts on some edges that Maya decided to be crazy about. We have a lot of art.
We do.
So yeah, I'm a numbers guy. So the last time I checked, we have about 150 square kilometers of player traversable space in our game, which is kind of weird for what is essentially a single player narrative linear game. It's rather, yeah, don't ask. So when we talk about big and we talk about some of the problems we're facing, we basically built a open world sandbox around a linear game, and then we built it out with all of this stuff. And we did this with a team that at our peak was like 110 people. And that's kind of crazy. And we, I know Joe's in the audience, so I'll just tell you, we did this with some of the best world-class VFX that I think any of us have ever seen with like 4 VFX artists for the entire game. We did 100 cinematics with a 7-person cinematics team.
And with the effects, that was Niagara, is that right?
Yeah, that's Niagara. So whoever at Epic was responsible for Niagara, Joe wants to buy you a case of beer. Niagara was amazing as both a high fidelity apparatus for us just to create. For those of you who haven't dug into it and you're still in Cascade, get out of the dark ages. Niagara is the future. You should lean in. It brings all the engineering things that you love about blueprints into VFX land, and it allows a small group of people to intelligently construct those things. Again, I can't even tell you how much extra VFX we built for ideas that we had. The game you see and the game we started at are very, very different. And despite the fact that my favorite Angry Cube is not in the game anymore, we had some really just cool and amazing things that the VFX team just kept going with. There's amazing stuff. I really wish there was a way for us to kind of put the cutting room floor up and show it off, because some of it's breathtaking.
Director's cut.
Yeah.
Okay, anything else on memory management? No?
Animation compression. If you're not compressing all of your animations, you're making a mistake. both from a loading standpoint at runtime. You really don't want to load giant animation files. And also just how much you're holding in. If you're running anything reasonable in your animation blueprints and you're holding a lot of animations, if they're not compressed, you're going to be hurting. Profile, profile, profile. I know everybody says profile early, profile often, profile on device. The other thing I will say is if you are not experts in certain facets of the business, we decided early on that our answer for some of the challenges we were going to have, especially as we leaned extremely hard on the GPU, was we're going to do upscaling. That's it. Our game is going to mandatory upscale. We have mandatory FSR upscaling on consoles. I am not an expert on a lot of that. So, one of the things we did was find the right co-dev partners. And for us, I partnered with Enduring, and I had known Adam and Kevin for a bit, and they brought in an incredible team. And so, I can't stress enough, we had some really incredible co-dev partners who helped fill in the gaps that we had. Those last couple months, and this is memory management where it's, hey, your HLODs take 19 hours to build and you're still getting numbers way outside what anybody expects. I could do the show of hands thing, like who knows if you built HLODs for your levels right now, what's your target number, what should it be? Yeah, that's the problem. Nobody knows that number. And so then how do you know if you're wrong or not? And so having people who can come in and say, I think that number should be 350 and it's 1350, we should probably fix that, is really important. We had a huge issue in one spot in memory where, and again, don't shake your heads at me over this, we decided to rewrite part of the material system, and I know that's a big no-no in Unreal Land. And actually what we did is absolutely amazing, and I will never tell Epic about this. But the side effect of doing that was that we generated a few extra shader permutations. And by a few extra, I mean 250 million extra.
Just a little.
Yeah. And so what that means is that the game may or may not have loaded like 3 gigs of shaders on consoles. So obviously that had to get sorted out. But again, who here off the top of their heads knows how many megs of shader memory they're currently using on any platform? Yeah. So finding the right people, either in your team as direct hires or as outsourcing partners, who can just look at that stuff and go, that number should be here and you're here and that's bad, or you're down here and you're missing something, will save you weeks to months. We had a very aggressive ship cycle, and our partners saved us on a lot of that. We would have gotten out eventually. I don't think we would have had the quality we had. I don't think we would have had the sanity we had. Some of us would not have the hair we still have.
I don't know what you're talking about.
Some of us. So, yeah, there's, memory management is huge. I could probably talk about frame rate for the next 20 minutes, but the talk's not that long, and I've already talked too much. So.
All right. Thank you, Mark. Yeah, no, that's a great, it's a huge topic, right? So it's important to get as much information as we can out there. We do have a couple more things we want to cover, but just a reminder, we are going to do some Q&A. So I can't really see anything, but there is a mic in the middle of the floor here. You can start queuing up now. We got a couple more minutes of stuff to go through, and then we'll get into that Q&A. So. Any other topics? Let me see, we've got a number of different topics here. But is there anything specific you guys want to get into with a couple minutes left here?
I know we talked a lot about the complexity of world partition and like, you don't have control anymore, go figure it out. There are some real positives about world partition as well. We made some tweaks in Unreal Engine 4 that in Unreal Engine 5, well, we don't have to make those tweaks in the engine. Don't tell anyone. Big giant comment blocks around it. We made a change to the engine. For example, that teleport actor, right? Like you have something here, something there. I need to have both ends loaded. In Unreal Engine 5, it was as easy as putting a streaming source component on each one and just overloading a function. And it was great. We didn't have to go under the hood and go make a change on our own. And likewise, to figure out, hey, am I done streaming? Unreal Engine 5, you have a public API with way more parameters and way more nuance than we had done ourselves in UE4. So there's a lot of tools there too, and certainly a huge progression from when we started on early access to where we are now. So there's a lot of good stuff in there too, in addition to all the gotchas and all the things to look out for.
World Partition essentially saved the level design team from having to do that whole step of setting up streaming volumes. You don't need those. World Partition handled a lot of that for you. You were just spot checking for Vista mountains that aren't loading when they're supposed to or whatever, which is great.
Yeah, it's usually,
huge time savings.
It's usually, designer or artist will try to look at it and like, what's going on? All right, let's have an engineer look at it, an engineer going, all right, where are all the references here? I know that something's pulling that in. And again, a lot of times it's just stuff that we told it way long time ago that the system just going through and is chugging through. It's not malicious, it's not trying to give you a bad day, but stuff happens and just breaking out the tool set and trying to figure that out.
Why the giant moons in the sky are creating like ridiculous clusters and super inflating our entire grid.
Yeah.
Because just assets that we had put in the early stages and just sort of viz dev, mountains and sky dome planets and things. We definitely had to go back and I had like a sticky note on my desktop that was like all the things you had to go back and uncheck in order to make World Partition happy for all of these assets, which in retrospect, moving forward onto the next project would be something that we'd actually build into sort of the asset import process so that artists didn't have to kind of do this, and our partners help us go in and really figure out why H-slots aren't building, like why the nanite, bad nanite ratios were just contributing to H-slots failing without telling us. And so you would be wasting, hours or days trying to build these H-slots. So there's a lot of stuff that we definitely had to go back and change at the very end, which starting all over, I think we have some really good best practices after all of our postmortems that we've done on this project.
Yeah, basically anything, we stepped in a lot of muddy puddles and ran into a lot of walls. And we've learned a lot from them with a lot of the bumps and bruises. But yeah, the planet thing, it was, we had a level that would just barf whenever you try to open it, and then you figured out, oh, World Partition is trying to figure out where to put this giant planetary object onto the grid. And one of our engineers found that and said, okay, don't do that, always loaded. And let's figure out where we have giant planetary objects in the level.
Alrighty, just a couple minutes left here. So, Mark, I would love it if you could touch upon the future of Ascendant Studios and the Immortals franchise.
Yeah. So Ascendant is working on an additional game right now. It is a spin-off of the Immortals franchise that is starting in 5.3. The core game is moved on to 5.2. We're getting that as we're prepping for release. We have New Game Plus coming out as Jason and his team are diligently working on that. There's a bunch of additional content coming with that. I got drunk last night with Adam, and he and I decided that we're going to actually move to 5.3 instead of waiting on 5.2 after looking at where the roadmap was. So my drunken decision at Unreal Fest is that I'm going to just expedite to 5.3 for our core project so we can basically maintain only one engine. So there's a lot going on for the studio.
Hot off the presses.
Hot off the presses. Sorry, Scott.
Love it. Okay, let's go ahead and bring up the house lights and move to Q&A. Does anybody have any questions?
the show. 3, get ready. 4, 3, 2, let's go, 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 go. On your mark, get ready, set, go, 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 go. On that jump, that get up and go, 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 go. On your mark, you ready, yeah, go. 4, 3, 2, let's go, 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 go. On your mark, get ready, set, go, 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 go. On that jump, that get up and go, 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 go. On your mark, you ready, yeah, go. show. 3, get ready. 4, 3, 2, let's go, 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 go. On your mark, get ready, set, go, 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 go. On that jump, that get up and go, 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 go. On your mark, you ready, go. Show. 3, get ready. 4, 3, 2, let's go, 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 go. On your mark, get ready, set, go, 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 go. On that jump, that get up and go, 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 go. On your mark, you ready, go.
All right. Good morning. My name is Chris Torne. This is my colleague Edward Dorobek. We're from Snapdragon Studios, and welcome to our talk about ray tracing on mobile. So we're going to cover two demos that we developed in-house at Snapdragon Studios. I'll be going over the first one, Artifacts, showcasing ray trace soft shadows. And Edward will cover our brand new Dragon Alley demo with Lumen, global illumination, and hardware-accelerated ray trace reflections. We'll have some time at the end for Q&A, so if you have any questions, just line up behind the mic. You might not have heard about us. We are a AAA gaming team inside Qualcomm. So we're working on the next generation of gaming technologies to enable the best possible experience for all of our massive user base across all our market segments, mobile, PC, XR, and automotive. So Snapdragon 8 Gen 2, which we announced last year, was our first part to support ray tracing in the form of Vulkan ray queries. So we started working on the Artifact project before 5.0 was officially released. And we showcased the demo last year at our annual Snapdragon Summit. It was running at 30 FPS in the Vulkan SM5 deferred renderer. But since then, we've been hard at work optimizing it, and it now runs at 60. So I'll show you what we did to get there. But first, here's a little video. So as you can see, the ray trace soft shadows make quite a dramatic impact on the visual quality. And so to implement support for the ray query shadows in the SM5 deferred renderer, it was fairly straightforward. So don't worry about taking pictures. This entire section is going to be recorded and uploaded to YouTube. But basically, the existing implementation uses ray generation shaders. So we just added a little bit of macro magic to turn it into a compute shader. You just have to be careful to use the right intrinsic so that it works for both versions. And this is the corresponding global compute shader, which only gets compiled for platforms that advertise support for ray queries, or inline ray tracing, as it's called in DX12 parlance. So it has a couple of extra compiler flags compared to the ray generation version. But for the most part, it shares the same exact interface, which means all the parameters are the same and all the plumbing with the RDG is kept the same. And yeah, this is the entry point I showed on the previous slide. And the last thing we need to do is just to issue the actual ray query. So that takes place in the trace visibility ray function. And so here you can see the original ray pipeline version with the trace ray call and the new trace ray inline that we added. Other than that, since Android didn't support ray tracing up until that point, we had to relax a couple of checks in the engine to make sure that some of those like ray tracing scene building was done, and advertise support for inline ray tracing and the Android DDPI, and voila, we had ray trace soft shadows running on Snapdragon. So that was for the deferred renderer. Now the forward renderer is, unlike the deferred, by definition, it doesn't iterate over the lights, so there's no like obvious place to compute the occlusion. So what we did is we made a simplified version of the render lights function that only computes the ray traced shadows. And so we inserted it between the shadow map rendering and the base pass for the forward path, which is quite a bit earlier in the frame than the deferred variant. And so we had to move a lot of the scene building earlier in the frame as a result. And since it's, you don't have a G buffer, so you don't have access to the world space normals, so you have to reconstruct those using the depth buffer, which gets produced by the early Z pass. Ultimately, we decided to stick to the deferred renderer because the gains we're getting were not compelling enough to justify dropping all the nice bells and whistles you get from the deferred renderer. One of our engineers actually made a port to the mobile renderer, which works in both forward and deferred mode. Again, this was an experiment, and we didn't pursue it further. In terms of performance, so out of the box, we were able to comfortably lock to 30 FPS, and 60 FPS was tantalizingly close, but we're not quite there. So all the timings I'm going to show you were recorded on Snapdragon 8 Gen 2, our latest flagship device. It's rendering at 1460 by 660 internally, and then getting upscaled to 2400 by 1080. So yeah, let's take a look at some of the optimizations we made to shave off the 2 milliseconds we needed to reach 60 FPS. So the biggest bang for our buck actually boiled down to basically a single character change. So the existing inline ray tracing passes in the engine, mostly for Lumen and some debug visualizations for ray tracing in the editor, relied on the Wave32 compiler flag. And they assume a one-to-one mapping between the thread group size and the wave size. But on our architecture, that results in at most a 50% GPU utilization. So by just changing the thread group size from 8x4 to 8x8, we got some pretty sizable gains. So we decreased the cost of the occlusion by 25%. Which brought the overall frame time down to by 7.5%. The next optimization we looked at was to try and reduce the number of ray queries in the occlusion shader. So even though we didn't use it, for the pixels that are tagged with the hair and subsurface shading models in the G buffer, there's an additional subsurface ray that gets cast. And because that branch depends on the contents of the G buffer, the compiler is not able to optimize it out. And so that resulted in instruction count bloat, and as a result, like higher GPR pressure, not enough room for the compiler to optimize. So by just wrapping it into pound if-def, we were able to remove it. So that used to yield massive gains, but shout out to our compiler and driver team who did amazing optimization work on their end. So in the latest drivers, it's only a 0.5% reduction in the frame time, but hey, I'll take it. But now that these low-hanging fruits were out of the way, we turned our attention to the shadow denoiser, which was by far the largest offender at that point. So just a little bit of background. So yeah, we're trying to simulate soft shadows, but we don't have the budget to cast enough rays per pixel to eliminate all noise. So here's what the magic that the denoiser does. So if we take a closer look, hopefully it's coming through on the projector, you can see that without denoising, yeah, there's quite a bit of noise in the penumbra. And this is what the denoiser does. But shadow denoising in UE is meant to be done by highly tuned plugins for each platform. And since Android didn't support ray tracing until that point, it fell back to the generic stock denoiser, which was not optimized for shadows. And so it took up like a whopping third of the frame time. So by contrast, if you look at a typical approach for a dedicated shadow denoiser, you start with a noisy binary input, and you compress that to a buffer where each UN32 is gonna represent the shadowing information for 32 pixels, so 1 bit per pixel. Then you run a temporal pass where you group those groups of pixels by 8 by 8 tiles, and for each tile you determine whether it's fully lit, fully in the shadow, or somewhere in between. And the pixels we care about are the ones in between, so that's the penumbra. So for each pixel in a penumbra tile, or one that's adjacent to a penumbra tile, you run a 17 by 17 filter that's going to give you like a mean shadowing for the pixel neighborhood. You initialize a variance buffer, and then you try and see if you can reuse some shadow samples from the previous frame. So you check for disocclusion by reprojecting your pixel into the previous frame, comparing the depth and normals. And if you can reuse the previous frame samples, you accumulate them, so you blend the mean and the variance with the ones you just computed. And to finish, you have a series of spatial filter passes that you run on the mean and variance images. So those have expanding kernel sizes, and you use the filter mean as the shadowing term for the next pass. And the filtered variance is fed back to the denoiser for the next frame. So it gives some pretty nice improvements to the image quality. So you'll notice if we zoom in that the generic denoiser outputs like really soft shadows, and some of the detail is lost. And we managed to preserve that detail with a dedicated shadow denoiser. It's also twice as fast as the generic denoiser, which is great, but we can do even better. So if we look at the typical implementation for this algorithm, the temporal pass is basically one giant shader with 4 sets of barriers, and it heavily uses shared memory. So what we did is we split it into 4 dedicated shaders. So the first one, the tile metadata classification, since it doesn't have to operate on a per pixel basis, since it's now its own dedicated shader, we end up saving a lot of redundant calculations by issuing or dispatching just 1 thread per tile. We also store the results in an image buffer rather than a storage buffer, which results in faster subsequent reads in the following passes. So with all of that, the cost for that tile classification pass drops down to 10 microseconds. Then for the 17 by 17 filter, so it's a separable filter, so we split it into a vertical and horizontal component. For the horizontal pass, the typical implementation will scan through all 17 bits and compute the weights as it goes, and those are fairly heavy ALU functions. So instead, what we can do is pre-compute the weights and store them in two 512 wide lookup tables. And so we take the leftmost 9 bits and the rightmost 9 bits, so that's 2 to the 9, 512, and we index into those two lookup tables instead of computing the weights on the fly. For the vertical pass, unfortunately, because we're now operating on the output of the horizontal one, which is floating points, we can't use the same kind of bitwise trickery. But by just converting it to use 9 gather offset calls, and outputting 2 pixels per thread, the cost drops down to around 140 microseconds, similar to the horizontal pass. For the temporal reprojection, we didn't actually have to do anything other than just like split it into its own dedicated shader. And the cost ended up being around the same, 270 microseconds, for a total of 550 for the entire temporal pass. For the rest, the setup pass was operating 1 thread per pixel, and it was using like subgroup operations to compute the one UN32 value that it outputs. So it ended up being a lot of threads just being wasted. So we instead dispatch 1 thread per 8x8 tile. So we actually output 2 UN32s per thread. And we do like 16 gather offset calls for the sampling, and so that drops the cost down to 20 microseconds. Finally, for the spatial wavelet filters at the end, the offsets for the expanding kernel sizes were passed in as uniforms, and so so that meant having to use texel fetch, which allows like uniform offsets. So by changing that uniform to a shader constant, we can use the more optimal texel fetch offsets, which requires compile time known constants. And instead of using shared memory and the barrier that comes with it, we leverage the fact that on our architecture, the texture pipe is highly optimized and it's blazing fast. So in this case, a more brute force type approach actually ends up being faster. So the cost of each pass basically drops down to like 310, 320 microseconds. And so basically we achieve 47% reduction in the cost of denoising. So that's more than a 4x performance increase compared to the generic denoiser. And thanks to that, the overall frame time drops down to like 14.4 milliseconds, which is nice. We have a few more avenues of optimizations that we want to explore for the denoiser. Most of them are like performance versus quality trade-offs when it comes to the size of the kernels or the shape of the kernels. We also want to see if we can, how we can extend it to support multiple samples per pixel, as well as multiple lights, ideally, while retaining most of the existing optimizations if we can. But mostly, one low-hanging fruit is going to be leveraging 16-bit half-precision floats wherever possible. As Edward will demonstrate in a minute, that can yield some pretty significant gains on our platform. So all the performance numbers I showed until that point were considering each optimization in isolation, but this is what happens when you put them all together. So we basically got a 28% reduction in the cost of the occlusion pass, 76% for the denoising pass, and that translates into a third reduction in the overall frame time. So we're now at 12.6 milliseconds, so comfortably in 60 FPS territory. So ray trace soft shadows on Adreno, that's available right now as experimental in UE 5.3. We're hoping that some of the optimizations that we covered are going to land in 5.4. Shout out to Carl and Jack at Epic for helping get some of those changes mainlined. In terms of future work, like I said, there's a few improvements that we want to make to the denoiser. We also want to revisit and optimize the forward and mobile render implementations. And there might be a little bit of room to get better concurrency by turning the compute shader occlusion to maybe like a fragment shader, and we might be able to run other passes at the same time on the GPU. But for now, I'm going to give the mic to Edward, who's going to show you how he took things to the next level with our Dragon Alley Lumen demo.
Thanks, Chris. Yeah, so I'm Edward. I'm going to pick up where you left off and talk about our demo Dragon Alley, where we were able to leverage Lumen and get global illumination running on Snapdragon 8 Gen 2 devices. After we showed off our artifact to the world and unveiled mobile ray tracing, we kind of had to ask ourselves, all right, what's next? We are kind of on this trajectory where every year we unveil some new feature where we kind of push the edge of mobile rendering, and we're bringing effects that people are used to seeing on desktop or PC, but they're running on mobile. So naturally, we kind of asked ourselves, all right, let's run Lumen, see how it works, see what we can do with it. And the spoiler is that we got the demo Dragon Alley running. It's a mixed outdoor-indoor scene running on Unreal Engine 5.3. It features indirect lighting, animated characters, dynamic time of day, and ray-traced reflections. Having all of that running in real time on mobile sounds almost too good to be true, so I'm just going to let the video speak for itself. Makes a pretty big difference, right? And it looks pretty great to me. And it's okay to be surprised by seeing dynamic GI on mobile hardware. I know I was at first. So, how can we have gorgeous state-of-the-art features running real time on a phone? That's basically what I'm going to cover over today. I'm going to go over how we use mobile ray tracing in the demo. I'll talk about some shader optimizations we made, and then I'll kind of cover how we handled our unique case of emissive lighting. So yeah, let's look at mobile ray tracing for the Dragon Alley. So when we were kind of first planning out the demo and conceiving it, we almost knew immediately that we couldn't use the entire full hardware ray tracing path. There are GPUs plugged into wall outlets that struggle to hit 60 FPS at 1080p on the full hardware path. A mobile GPU on a battery is going to have an even tougher time to reach that target. So we're going to try and prioritize certain effects over others. On the screen, you're seeing the difference between hardware and software ray tracing for just diffuse and direct lighting. And it's okay if you can't really tell the difference. That's kind of the point. For mobile content, it didn't shine as much. It's not to say that it's not useful, but it definitely did not warrant such a huge performance hit. Meanwhile, hardware ray traced reflections had massive benefits. You can kind of see on the orb that in the hardware ray traced version, there's all sorts of details that are being resolved, like the cloth or the flags that are hanging. So we decided to focus on off-screen shadows and reflections for hardware ray tracing. Meanwhile, all the performance-critical sections, we're going to rely on software ray tracing. So when we first started to enable Lumen running on Android, it was actually surprisingly easy. There's been a massive effort to get desktop-level features supported on mobile. And basically, that meant no porting work was needed for us. We basically just flipped a switch in a config file, and Lumen was running. Performance, though, was a different story. When we first kind of ran Lumen at our target configuration, it was taking over 60 milliseconds alone per frame. And almost all that time was spent in the final gather. As a result, we were basically running at 10 FPS. That's obviously not acceptable if we want to have a playable frame rate, and we don't want to burn our users' hands within the first 10 minutes. It's not a horrible place to be in, though. A little over a year ago, running Lumen on mobile just kind of wasn't even on the table. So most of the improvements were made for console, PC, and we just need to give it a little bit of attention. That's where we stepped in, and we're going to see how fast we could get Lumen to run, and I'm going to give you some highlights of the optimizations we made. I'll warn you, the discussion's going to get in the weeds, but it yielded really dramatic results, and I want to show it to you so maybe you can use it. If anything, I want you to take away that if you're just willing to be cerebral about mobile hardware, you can get massive performance uplifts with pretty little work. But before they do that, I want to talk about how we measure performance, and that's where we use the Snapdragon Profiler. So this is a graphics profiler that we've developed in-house, and we also have a version available to the public that you can download. It's got a lot of great features. My favorite one is the offline shader compiler, which will give you statistics about the shaders in your games, like the instruction count, the number of texture samples, like buffer reads, everything. We also have GPU performance counters. We give you insights into tiled rendering, and we even support API traces for OpenGL and Vulkan. So like Chris said, one of the biggest optimizations we looked at first was converting all the Lumen shaders over to use 16-bit data types. We've supported these natively on mobile for a while, and they have massive benefits. The first one is we can effectively double ALU usage. So that means that we're doing twice as many operations in the same amount of time. The next big one is that when we use 16-bit storage types, we're cutting bandwidth and storage in half. Bandwidth is really power hungry on mobile, so this is a huge one for saving battery life. And it also kind of lowers the pressure on the shaders, and so as a result, the driver has an easier time optimizing. The problem though with 32-bit conversion to 16-bit is that we're going to lose precision. To give you an idea of what that precision loss is like, I'm showing you the quantization error for just small values. So you can see between 0 and 1, it's pretty manageable, and you can expect quite a few decimal places of precision. But as your data grow, it quickly becomes kind of untenable to rely on precision. So that means you have to be cautious about what data you're going to convert over to 16-bit. Things like RGB intensity, radiance, local space coordinates, those are all great. They're small numbers. Meanwhile, you have to be a little careful about things like world space or depth. In special circumstances, you can get away with keeping them 16 depth, but it's just a little more difficult. If the precision loss does start to affect image quality, there's mitigation strategies that you can use and that we can use. So the first one is to use the sign bit. So what I'm not showing you on this graph is it's actually symmetric. So precision is really good between -1 and 1. So it might seem unorthodox, but you should turn data to be maybe negative so you can leverage that precision. Keeping data near 0 in general is also a really good idea. So maybe if you have facial animations that you're working on in a compute shader, maybe locate the data origin on the center of the face instead of the body or somewhere else. And then sometimes maybe the shader work just has to be in 32-bit because you're losing too much precision like in the shader. In that case, it's still a great idea to store it as 16-bit because again, you're going to save on bandwidth. These were a few shaders that were amenable to this conversion. And you can see it's not uncommon to see utilization gains of 25% or more. And some of these shaders, we were able to cut their runtime in half or more. All right, the next thing we had to look at was balancing the texture load of Lumen. So Lumen is very, very texture heavy. And that was kind of a problem for us on mobile. We were seeing peak bandwidth of 11 gigabytes per second or more. And a lot of our shaders had 50 individual texture samples in them. That's not counting ones that are inside loops. So when we got lots of texture reads and really arithmetic heavy shaders, we kind of run into this vicious cycle where they can't get the texture data right away, and then they have to wait, and then they're getting starved by the texture pipe, and we get this extreme cache thrashing problem. Before we optimized, we had issues where 95% of the runtime of a shader, at least one thread was stalled. So the first thing we looked at was trying to manage occupancy. So like I said, when you have a lot of individual threads competing for the same resources, they start stalling each other out. So I'm going to give some advice that's kind of counter to what Chris said and instead lower the group size. In one case, we kind of saw a 70% reduction in the runtime by doing this. And basically the main reason is that we can lower kind of the number of active threads that are running. They aren't going to be competing over as many cache resources, and they're able to keep doing what they want to do. This actually isn't kind of uncommon. A few people who have done sphere tracing algorithms have kind of found out that, yeah, keeping lower group sizes is a good idea because texture cache misses are kind of an acute problem. I know it sucks to kind of hear counter advice from both of us, but kind of my response to that is every shader is unique like a snowflake. They've all got different performance characteristics, and you're just going to have to stay diligent about profiling. All right, the other thing we can do is we can try to leverage the texture pipe. Like Chris said, it's really fast, so sometimes converting buffer data over to textures, especially in shaders where the texture unit's not being fleshed, you can get some massive gains. Similarly, if you're using textures a bit too much in a shader, it might be a good idea to consider using a buffer instead, especially if that data is less than 16 kilobytes and you don't need to sample it with filtering. You can fit it in local memory and it's really fast. All right, the next thing we had to optimize was distance field tracing. So Lumen does this great thing where the global distance fields are arranged in clip maps, so we can keep storage down low, but then prioritize resolution near the viewer. The problem for us was that we would have individual traces in a thread group reading from different clip maps, which are not contiguous in memory, and now they're all, again, fighting over memory resources. So the solution here, we just place a group barrier after each clip map, and we don't let any ray traces go past it once they've all looked at that clip map. And it brought down our L2 cache miss rate in our best shader down to 1%. It seems a little weird because we are stalling threads artificially, but that's much better than doing it because of a weird texture cache issue. The other problem with distance field tracing is we'd have this long tail problem. So in an individual thread group, all the ray traces would be done. And then there's just this one trace that does not want to finish, and it's taking up 80% of the runtime. And in that case, when that trace shows up, we just axe it, we get rid of it, discard the result. And we know it's kind of okay to do this quality-wise. Lumen already does it in screen traces, for example. And it's a great way for us to kind of bring up performance, but not actually hit visual quality. Okay. I'm going to move on now to talk about how we handled emissive lighting in the demo. So some of you might know that emissive materials are great in Lumen. They're basically a way to light your scene with no additional cost. But there's a limit to how bright and how small they can be before you start to see some noise artifacts. So in our demo, we had all these bright lanterns in the scene that we wanted to light it up during nighttime. But when we're running at the target settings for mobile, we would get really noisy patches that you can see inside the yellow circle. And it would also kind of not temporally filter as well as you'd want, so you'd get these light boiling artifacts, and it was really distracting. The other issue with this undersampling problem is that we would have these underlit areas in the scene that were far away from the lanterns. So upon ocular inspection, you look at this and you say, those lanterns are really bright, why aren't those areas being lit? And this was something that we needed to handle. So what do we do here? Can we just increase the sample count and the probe resolution? It'll work, but again, we're on mobile. The last thing we need is to increase the scalability settings and get us into a point where we're back at that 5 to 10 FPS range. We could just convert these to area lights. Lumen, handles lights especially. But again, kind of weird. We don't want to convert a mesh into a light and fake it. That's not something we want. Part of the great thing about Lumen is the workflow is really nice. And again, Lumen also only supports a maximum number of lights, and each one would cost us an extra 300 microseconds. So we had to do something better. We had to add some Lumen extensions to maybe handle our special case. Intuitively, it seems weird that we're having this problem. We know that this mesh is really important for lighting. We know exactly where it is, and yet all of our radiance cache probes are supposed to indirectly just pick it up. And we are only going to rely on important sampling. Instead, we decided, okay, let's just explicitly sample the mesh after doing all of our tracing operations, so that way we know for sure this emissive mesh is going to be lighting our scene. To do that, for any radiance cache probe, the first thing we had to do was just find the nearby emissive object. Then when we do that, we take our potential sample and we need to make sure it's not going to be occluded by any objects. And last, the easiest thing, just accumulate the sample into our data. But before we did that, we kind of needed to know how we plan to sample meshes. We want something that's going to scale with the size of the mesh, but not the complexity. That way, we don't have some high poly emissive mesh that's just going to immediately tank our performance. Thankfully, Lumen already kind of parameterizes the scene via the surface cache. Some of you might be familiar. These are the card captures that happen in Lumen, and they contain things like material data, the normal, the color, and best of all, the emissive. So we can just look through the scene, find the emissive cards, and rely on that, and we'll stay consistent with the rest of Lumen lighting. So let's kind of look at how we do that. The first thing we need to do, find the nearby emissive objects. We were like kind of worried because sometimes doing a nearest neighbor search can be really expensive. And we experimented with some data structures, and the first thing we found out is there's really actually not that many emissive cards in most scenes, especially not ours. And so instead, we just store all the emissive card data into a flat buffer, and we exhaustively search through it for every radiance probe. All we need to store is the sample position, the sample itself, and just like the position of the axis-aligned card. This is a really small buffer. It was only 8 kilobytes, and so as a result, fits into shader local memory, reads are coherent across threads, and it was blazing fast. The next thing we needed to do was determine if the sample would maybe be occluded by some mesh that was in the way. So in this case, normally what you do is just cast a shadow ray. But again, the last thing we need is another ray trace operation. So instead, we have a bunch of previous trace results that we can just do an inverse lookup of and maybe see what that was and if it was actually closer than the emissive card. This gave us some light leaking problems, but basically what we did was just kind of check the angle between the two rays. If it's too big, we'll just discard the result. And then the last thing to do is just accumulate the final sample into our data. We did kind of throw an artificial fall off to make sure things too far away weren't being too lit. It seems kind of weird to do this. Like we've got this rectangular kind of source of light, and we're basically just treating it like a weird point light. But in reality, like the small emissive meshes that we're trying to handle kind of have the same lighting characteristics of a point light anyways. And then the larger ones, though, are going to have more cards in the lumen scene. And so naturally, we're going to give them more samples, and you'll see more area lighting like effects. So to show you kind of what impact this made, let's take a look at that noisy image we were having some issues before and add explicit emissive sampling to it. And now it looks like the brightly lit scene we'd kind of expect more in real life. And the rest of the scene is actually being lit by this very bright lantern. There's another problem area where we had this basket of fruit that we wanted to be lit by an emissive light. And again, you look at this and you're like, wow, that lantern is so bright, and I cannot see those fruit right next to it at all. Maybe just a little bit, but it's nowhere near as bright as it should be. If you had the sampling on top, okay, great. Now I can actually see the fruit, and we know the occlusion is working well because light is not leaking in between the crates and underneath the bench. The best part about this, the total cost of this extra step was only 300 microseconds. So we kind of went in the opposite direction in terms of optimization. But doing this meant we got way better quality results, but without increasing sample count, doing any extra ray traces. So this was a huge one for us. When we kind of brought all of this work together, we cut the lumen's frame time massively. What was over 60 milliseconds was now just a hair over 8 milliseconds, which is kind of the original target for the lumen epic settings. And now we're hitting it on mobile. And it means we get gorgeous real-time lighting on Snapdragon devices. I know Chris and I covered a lot, and we moved kind of at a breakneck speed. But kind of the one thing I want to be clear is that the landscape of mobile rendering features is moving really fast. It's accelerating. It's come a really long way. And we're kind of showing it best off with Snapdragon 8 Gen 2 on Dragon Alley. I think with Unreal and our mobile devices, the future of mobile games is going to be really stunning. It's going to be exciting to see what game developers are. I hope you share that same excitement. I want to acknowledge a few people that kind of helped us make this happen, especially our art teams. They kind of took on the challenge of pioneering, designing and developing the first mobile ray tracing content, which, as they know, was not a very easy thing to do. Yeah, and so thanks for everyone to coming to see what Snapdragon Studios has been working on. If you kind of want to come see these demos running on device in real time, we're just outside in the expo hall right in the center. You can also talk to us if you're interested in optimizing Unreal Engine 5 on mobile. So please come by, and if you don't ever see us in the conference, you can email us at sgs@qualcomm.com. We'd love to hear from you. And yeah, Chris and I can take the remaining time to answer any questions you have.
show. 3, get ready. 4, 3, 2, let's go, 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 go. On your mark, get ready, set, go, 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 go. On that jump, that get up and go, 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 go. On your mark, you ready, yeah, go.
thank you guys very much. Thank you. Thank you, and I hope, is everybody having a good time at Fest so far? You know how I do it. Come on, bring it up. Is everybody having a good, all right, there we go, yeah. Well, thank you guys very much for joining this one. I'm really excited to have this conversation, and let me tell you why. Unlocking creativity, what does that mean? A lot of times we're kind of, we put ourselves in these boxes, and we have to tell a story in 22 minutes, or we have to tell a story in 90 minutes, or you have to tell a story in all these different ways. But I think that there's something that is happening right now because audiences don't necessarily want to just tell their stories in that one way. They actually want to extend, and they want to participate, and then they want to hear the richness of the story and then immerse themselves in that. And what that means is that there are new opportunities. Just like when streaming came around, there were new opportunities to not have to do something in that one amount of time, but no, you can let your story sing. You can let it breathe. You can let it do what it needs to do to really tell your story. And that's the conversation that we're going to have up here today in talking about how can you unlock, how can you start to reach into other areas and engage your audience and tell your story and give them an opportunity to actually participate. So with that, I'm going to introduce the members of the panel that we have up here. So Jason Chen, executive producer, has done some amazing things in this space that we'll see in a moment. We have Kevin Dart, who's the CEO and creative director at Chromosphere. We'll talk a little bit about that. And then we have Alton, who's at GRX Entertainment, who's also an awesome director, someone who is also bringing up and sharing his knowledge with the youth and starting to understand the audiences of our future. So what I'm going to do first is I'm going to show a little bit of a clip from Jason's recent experience, and then we'll get into this conversation. Just so you know, I'm going to kind of do that as we go down to give you guys just a little bit of information on who everybody is. So. All right. So
that's a lot of work.
It is. Awesome. So Jason, just really quickly, can you tell me a little bit about what we just saw there?
Sure.
How was that? What was going on? Because I think we saw a couple different things there.
Yeah. So essentially what you all saw was a traditional way of linear content in the beginning. So normal animatic scenes, cut scenes, running through a traditional Unreal-based animation workflow. So we used motion capture from the early onset, did facial capture, and then ran it through an animation pipeline rendering fully out of Unreal. So, and as we kind of continued forward and the opportunity arose to start dabbling into the UEFN experience, we had all these amazing assets that we had already created that were made for the engine, and decided to take a stab at creating that same world within the UEFN market, UEFN world. And it just kind of made sense because we had the assets, we had the ecosystem, we had to do some alterations to the environment to fit within the island, but it was still, we had all the assets, and the amount of time that it took to push something out, an actual playable game, was so exciting. I think it was a span of probably 4 to 6 weeks, which is unheard of. And then as we kind of move forward, the traditional, we did a test for traditional console gaming or PC gaming. That's when you saw the ferry kind of flying around all these different environments. And the real goal of that was to prove that we could still use the cinema grade assets into an actual interactive space. But then the challenge was brought up to see how we can really combine, and this is where we kind of see the future going, and I think we're in agreement that in the future there has to be a way to engage audiences from content to interactive gaming and reward each of those processes, creative processes. Because as we all hate, you know, there's a huge gap in between seasons. So our job as a creative is to make sure that your player or viewer stays within your IP longer, making that time in between, the gap in between seasons or different versions of the game as seamless as possible. So that was really an idea that we worked hard on to see how we can essentially reward viewers for watching through an entire episode or movie, and then you see rewards in the game. And then if you, the player, want to actually play through the entire game, you get rewards with additional content on the viewer side. So trying to really balance that out.
The interesting thing to me here is that, and I don't want this to be lost on the audience, is that this is not normal. So meaning that generally linear content is made and you make it shot, shot, shot. You are building cities in order to then tell your stories in that city, which naturally allowed you to go into the experience like UEFN and allow you to go into games, which is actually the essential components of a franchise, right? A franchise, you're able to engage in all of these different areas,
right.
And usually that's something that is very difficult. Like you need entire companies to do either one, and they don't always want to work together. So it is impressive to see with a relatively light lift, you're able to do that. So I want to move on now to Kevin, and we're going to show a little bit from what Kevin has been up to. So Kevin, I'm going to continue in this kind of thread of you guys have also been doing and using the engine to make some great content. Here we see Yuki 7 and Mall Stories and things like that. And you're also starting to take this and get in and extend into UEFN or extend into other spaces. Tell me a little bit about your guys' approach to that.
Yeah. I mean, just for some background on our studio, like we're a very small outfit. We're mainly a group of 2D artists and 2D animators who have kind of dabbled in 3D in the past and are really interested in 3D. But until we started using Unreal, a lot of the work we were doing in 3D just wasn't really feasible for a studio of our size. And I feel like working in Unreal, we've been able to really stretch what we're able to do and play with new styles and experiment a lot. And this started around 2020. We started getting into Unreal. And as we started working in it, we were just getting more and more interested in the process and what we could do with it. And so it started expanding out where we were seeing what we could do with this character Yuki 7 we had, and then eventually expanding to this Mall Stories short film that my wife Elizabeth Ito came up with. And then now a lot of the stuff you saw in there is from some of the new Yuki 7 content we have coming out soon. And we're also going to be showing more about that at a panel here later today at 2 o'clock. Just going to plug that. It's called Into the Yukiverse if you want to check it out. We're really going to dive into like how we're making a lot of this stuff and what's going on there. But yeah, we've also just recently started to get into some of the UEFN stuff, and we made, you can actually get this now on the Fab Marketplace. We built a Mall Stories mod kit. Where you can get all of the assets we used to make the mall. I'm talking about this film that wasn't in that clip at all, but if you look it up, it's called Mall Stories. This kit on the marketplace is called Tropico Hills Mall Kit, which is the name of our made-up mall. And we're really interested in people starting to get this kit and play with it and create their own stories or worlds or just some arenas to have their characters shoot at each other or whatever. I don't know what they're going to do with it. But yeah, it's really interesting. It's a really interesting platform, and it's great for a small studio like ours to just explore and see what we can do with like really small teams of artists.
Mm-hmm. So, and in this same vein, I'm going to go down to Alton. And Alton, always impressed with the stuff that you have going on, especially you're thinking about, okay, hey, what's that next thing? What's that next vision? How can I tell my stories? But you also share. You share a lot with also some of the youth that is coming up. And the thing that I think that is just so beautiful about that also is that that's actually what the future of entertainment is. And it's clearly not what it was in the past. So before I have you answer anything there, I'm just going to play a little clip that is going to show some of the work that you've been doing. So for me, in looking at that and hearing what they've been talking about here, accessibility is the thing that jumps out at me, is that all of a sudden we have teams in the two of them, and you also have youth that are coming up that have access to the same tools that, as I start to think back, were really limited to a very small number of people who had a lot of money and were somehow allowed through a door in order to have access to that. And it was a very gated way. Can you talk a little bit about what you're starting to see from the students you have and the difference between how you were coming up and what you're seeing that they're doing?
Wow, I think one, I start with how it made me feel when I first started. As a director, usually you just get the tools, right? And then you work with teams. But I was really curious about what was under the hood. And when I was doing this project called The March with Time Magazine, when we were recreating Dr. King, they were using Unreal Engine. And then I got into the fellowship, really curious about how can I learn how to use this. And the key thing was I felt empowered. And I was like, wow, if I can do this, I want to share this with everybody, right? Mm-hmm. Because now it gives people access to, I've seen the youth use it in ways I haven't even thought about. And not only that, they're already sort of working and playing games and things like so, especially they already totally get it. And I've seen them jump in there in 2-3 weeks. They're in sequence of like, I need to learn more. And I'm seeing them create these amazing experiences. So that's what really inspired me to build like an accelerator as an extension of our company, to build an ecosystem where those opportunities could continue to grow and we can have a knowledge exchange and be empowered by these tools.
Mm-hmm. So now I'm going to bring this to everybody. So the thing, again, that I want to kind of strike to is this ability to move between these different verticals. I remember, again, I'm going to go with my gray beard and my oldness here, but when I started, there was this certain passion in the early 90s, and the passion to do something, to put an image on the screen that had never been seen before. But there was also a certain academic component to that, of you had to be a computer science or a pretty hardcore animator in order to do that stuff. I think that for a little while there was this kind of lull in that, and unfortunately we got to the paint by numbers kind of thing. I'm seeing something right now, though, with this passion again. And the passion seems to be built around gaming, both vocabulary and gaming approach. So, and what I mean by that is, again, I'm used to, if I'm building a story, it's a shot, it's a shot, it's a shot. But you guys are approaching things from the perspective of, I'm shooting footage like I'm in a video game. And there's physics that are happening that you have made happen, and you're using that physics to approach storytelling like a video game. Kevin, can you, I mean, what do you think about that? And is there anything to what I just said?
Yeah, I mean, like when I've described to people in animation what we're doing, sometimes I get a lot of confused looks about how we're approaching story, like how we just kind of go into Unreal and start planning things out. But when I talk to people in video games, like I have friends who still work in cinematics for games or whatever, and they're like, that's how I've been doing this the whole time. Like, you guys should ask me how to do this. So it is like I think a lot of the process and the thought behind it does come from games, and we have started to. There's a new iteration of the mall story shorts we're doing now where we're bringing in guest directors, because so for the first few iterations of the stuff we were doing in Unreal, I wasn't personally doing a lot of it in there, and I really related to what Alton said about the experience once you're in there. Like this last summer, I spent a couple months in there laying out the new Yuki 7 shorts that are coming out myself, and luckily some of the members on our team like gave me a crash course on how to do it all, and I kind of became obsessed with it, and I was like, this is so fun. Like, it feels like you're just playing with toys. Like, I kept describing it like when I was a kid, I would try to make little short films with my Legos, and I would have a camcorder and try to set it up and get these like really cinematic shots and stuff. But it was always impossible because like they're too tiny and the depth of field is like really tricky and everything. But you can do all of that in Unreal, and it's a blast. And so we're doing a new series of shorts with mall stories where we're inviting in guest directors who've never used Unreal before, where we've set up the mall for them. They have the characters there already. And in about 20 to 30 minutes, I can give them enough of an overview that they can get in there and start laying out their films that they want to make. And pretty much anyone, like, we always ask them, like, have you ever played like a first-person shooter type game or anything like that on the PC? And like, as long as they have that baseline knowledge of like being able to move around in a 3D space with a mouse and a keyboard, we can pretty much get them up and running in Unreal in like no time. And to me, that's the most exciting thing about it, like getting this kind of innovation that can happen when you bring in new artists with with a fresh viewpoint on it, and they start playing around. And it really is just play. That's what I keep saying about it. Like, this is fun. We're just playing around and experimenting, and that's kind of how you get to like real innovation, I think.
There's something I always say, and I'm going to say it to the three of you guys right there. There's nothing to it but to do it. And that's the one thing I think that right now is fresh and new, because again, animation has always been this kind of thing where it's like, there's one shot a day that's coming out, or a week or something like that, and it's just like it's a team thing with all these different. But what you're talking about is you're talking about turning something over to someone who has no experience with it, and then they can just treat it like the real world or treat it like a video game. And that's a really exciting thing. Jason, you actually, when you guys were contemplating Gossamer, I remember that you guys were also talking about a linear story, but maybe approaching it from a non-linear way, so that the story still plays, but you're able to play that story out and get information from other areas.
Yeah, I mean, when we were thinking about, so as you kind of touched on, the linear content, linear animation way was, okay, you see in the script, interior day office, right? Or interior office day. And what we would generally do is just create those 4 walls, and that's it. But with the speed and efficiency now, and with things like multi-user, and we were, at the time was lockdown, we had to adapt, we had to figure out what to do. But knowing that we were working within a game engine, we were forced to think about, okay, so we have a lot of efficiency here. Instead of that, why don't we build out this main staple, this main environment that we know we're going to come back and forth to time and time again throughout an entire series, and see what kind of comes out. So we had massive amounts of concept design and art, and Rob Vincent, two-time Academy nominated production designer from the live action space. We actually brought, and you're talking about education too, it's kind of flipped itself now. It's like now there's such an appetite for these amazing, talented on-set technicians to understand what we're doing. So I think it's really a responsibility for us that understand it to relay that knowledge to them, because they're just as excited at creative freedom as we are. So anyways, we came in, and now as we started to go through and have specific scenes that were scripted out, we could actually now go in and do a virtual scout. So the approach was, okay, let's build the Universal Studios backlot first, and then see where all your scenes fit in, which is a completely ridiculous notion, but what it did was it allowed us to play with camera placement, it allowed us to really play with lighting all at the same time. Even though there's different departments, throughout a pipeline, you can actually see how they're all syncing up together. So for me, it was probably the most creative process. And to touch on what you had said too, it is fun. Like, it's a lot of fun. And just to put some context out there, I mean, the fact that there's so many tools that are built in within the engine, like virtual cameras. On the first Avatar, we had to have an entire mocap stage, 8 operators to get a virtual cam working, daisy chain to everything, and it was in an entire lab. And now, last year, we did a VCam demo at Unreal Fest with a laptop and an iPad, and we were able to shoot a ton of camera coverage, helicopters in that same environment. So, the tools are literally in your hands. You can go out and shoot VCams on your iPhone right now, and it's just shocking. Really, really fun. At the end of the day.
Alton, is there anything that, with the students that you work with, is there anything that you're seeing in terms of approaching things from a game making point of view? And I'm going to say that because, again, coming from filmmaking, everything you set, everything you do, you don't take advantage of physics or any, like you were saying, like a world or something. Are there things that you're seeing in your students and what they're doing that is, just an approach that you're like, whoa, that is way different, but it's way cool?
Yeah, I'll say 2 things. One, since I had worked for about 7 years in XR, like VR and AR, seeing some of those creators jump into the engine and it becomes sort of like native to them, because now those tools are available in Unreal, virtual scouting and things like that. That was one big one where they came in, set that up, and they're already thinking spatially. So being able to set up the VCam now was much easier for them to get in there and get their shots, set up the VR goggles, going there, looking around. I thought that was pretty amazing to see how all that could come together so quickly. And then 2, they're going in and they're just kit bashing worlds that's just like insane. I remember one guy, he was a graduate from Hollywood High School, a guy named Tommy Escobar, and he came to help the high school students. But he had been in Unreal 30 days, and he recreated, we bought him this scene, like this driving scene. He recreated the Children of Men fire crash scene, rebuilt the whole scene, virtual camera, car fire. I was like, man, this is insane. 30 days, first time.
And wait a minute, he had just gotten into the engine recently?
He had just gotten into the engine. So he reached out again, said, hey, I'm gonna write, he wrote me a letter. I wanted you to give me an apprenticeship. I was like, okay, well, come on over then. And then he set up the Nintendo Switch controllers now, dialed them all in. I was like, this is pretty impressive how he just got into it so quickly. So seeing things like that, like they're also helping us now, you know what I mean? Do things as well. So it's just pretty cool and impressive to see how empowering it is.
So, Kevin, there's a story I remember hearing your wife tell about, I guess you guys had set the people, the extras that are in the scene, and then you had a shot where you're talking to the main character, but then one of the extras walked in between the camera and the person, which would never happen, is really weird. But can you tell me a little bit about that? Because you guys left that actually in.
Yeah, we love, I mean, even when you're doing art, you don't want it to feel stale, and anytime you do any kind of digital art, you're always fighting that digitalness of it, that thing that makes it feel not natural. Like, you want it to have this human touch to it. And we've been looking for ways, anything we can kind of capitalize on in Unreal that feels like that. It feels like accidents, or it feels like things that would actually happen in real life. And my wife Elizabeth, so she's the creator of the Netflix show City of Ghosts, and she was also brand new to Unreal and always looking for, she finds a lot of humor, and I do too, and like when computers go wrong, like that's like there's just a lot of fun to be had in seeing when computers make mistakes. And but it's funny when it mirrors things that we would do ourselves. And so the whole concept behind Mall Stories was that it was based on a real restaurant at the Burbank town center that her and I used to go get dinner at late at night when we were working at Cartoon Network together. And there's just a lot of character to the restaurant, and the food's amazing. And so during the pandemic, we were just talking about malls, and she was like, I wonder how the Mongolian Grill is doing. And so we went out there and asked, like, hey, could we make a film in Unreal about you guys? And they were like, okay. And I think Minnie from the Grill said she didn't think we were serious, and then she was confused like a few months later that it was all done, like we had actually made it. But yeah, it was based on real life, real people, and we wanted to create a sense of this mall being a real place. And it was really kind of like an amalgamation of all these malls that we knew from our past. And we also visited a lot of malls in the LA area and kind of combined it all into this one place. And yeah, part of that character is setting up people who are just regulars at the mall. And so we designed like some mall walkers and some kids to be playing by the fountain and stuff like that. And then Teresa, our technical art director, figured out how to set them all up on these paths to randomly walk through the mall. And then every time we took a shot when we rendered, it would be a complete accident. We wouldn't have any idea what the crowd would be doing in that shot. So we would get people randomly stopping in the center of the frame and looking at their phones or something, or like walking in front of the camera or whatever. And we actually try to keep every one of those things in there because it just adds such a sense of fun and reality to it and naturalness, because that's kind of how real life happens. And yeah, it's just fun.
That's really funny to me because, knowing animation, that's in many ways a no-no. You know what I mean? Like, there are these things that if someone was to say, okay, yeah, so I'm going to have this person stop in the middle there, then you'd get a pink slip if you were.
Well, there's so much. There's such a drive for perfection that you see in so many modern movies that I think a lot of them are starting to push against. Like the new Turtles movie, I thought was just incredible because so much of the aesthetic of that movie was embracing accidents and embracing like not having everything need to be completely perfect. And that's what we're always chasing too. Like you don't want it to feel like everything is planned out and scripted, or you get something that's very stale. And yeah, I mean, like at some of the bigger studios, they'll have entire teams dedicated to animating crowds. Like I remember hearing about that when I was working in feature animation. Like, oh, that's like a crowd group problem or something. And there's like a team of like 50 people that just animate crowds. And I was like, how is that possible? Like it didn't compute to me, just with like more of like an indie animation type mentality. And so to me, the crowds thing and that we did in All Stars was also just a huge time saver, because like you don't want to have to think about that. Like this is something that's in the background that isn't really important to it, but it's meant to just make it feel alive, give it some character. And so yeah, it's just a fun tool to get that out of.
Let's touch on economics here real quick. Usually a lot of the things that we've been talking about up here are big budget and big ticket items, as I said. And there's something right now that is kind of reminding me of the music industry when Napster came around and turned things upside down, and then there started to be marketplaces in place where musicians, if they didn't want to go for the traditional thing, they had the opportunity to take on their own business. So being that you guys are starting to play in all of the spaces, meaning in the linear, I'm going to watch this thing on a flat screen, I'm also going to do an experience or a game, and then also I'm going to sell things on Fab, and which is new, right? I mean, that is something that's very new and just starting. What is your guys' thoughts around that, and how does that impact the businesses that you have?
Oh, I think the great part about that is it opens up the door for creative entrepreneurship, which is a big thing that, we really believe in. And it allows people to take their transferable skill and find a place in that whole ecosystem. So when you're talking about, like, we have a team that started off learning photogrammetry, and then now they're creating assets and they're licensing them out and selling them to other creators, and they're connecting, and they're building. So I think it's a great opportunity to leverage a lot of those tools with your skill set. And even if you don't want to start a business, learning how to think like one with all these tools now allow you a great opportunity to flourish in this, immersive economy, so to speak.
So I'm sorry, these are kids that are?
These are actually, yeah, like one of the, we have one of our first apprentices. She came from North Carolina A&T, a young lady named Reagan Brown. And when she graduated, she said, hey, our program, she said, I want to stay here and work here. I said, no, Intel offered you a job. You need to go over there and, build. And now she's working and helping lead their virtual production and growing their ecosystem with what she learned. And she came from VR, and she's a computer science major. But now she learned Unreal Engine and took that over to Intel, and now she's getting them acclimated to virtual production and bringing her transferable skills. So things like that. Now, economically, she's grown. Right?
Right.
So those types of things, I think, are really amazing, that now she can share and be an evangelist and grow that and create more opportunity for herself and others.
It's amazing to me also because this has just happened. And so it's amazing to know that people are having that opportunity. And I am talking to y'all. But anyway, I haven't even introduced myself to y'all, and I'm still talking to y'all directly. So that's just how I am. It's okay. So anyway, I'll open up to the rest of you.
Yeah, I mean, oh, sorry.
No, go ahead.
I've had a lot of people ask me, like, so is it cheaper animating in Unreal? And it's a difficult question to answer because there are things that are streamlined about it. It streamlines parts of the process. But the fact is, like, you still need people making all the creative decisions. You need people designing things. You need people building things. You need people doing all the stuff. And it costs money. It costs money to make this stuff. I mean, we're such a small studio, like comparatively, our budgets are nowhere near like what you see from features or the big game studios or anything like that. But it still costs money at the end of the day to have artists doing this work, to be innovating. And we've been so incredibly lucky to, all of the work that you saw in that reel has been funded through the Epic Mega Grants program. We wouldn't have been able to do it otherwise. But also a big part of why we were able to do that was because of the support of one of the producers at Epic, Karen Dufalo, who was let go in the layoffs last week at Epic. And so something I've found running a studio is that you can have all the talent in the world and the best portfolio in the world, but you still need someone on the other side who is able to champion for you on the business side. And Karen's been that for us for 3 years. She saw value in what we were doing and thought it was worth helping get us into this program, and thought it was worth funding. And we've been able to create all of this stuff and learn this process and build this Unreal pipeline thanks to her and the mega grants. And but yeah, I don't know. I'm not sure what the future holds for it, because I mean, in general, like at any time, it's hard to find funding for artistic innovation. It's hard to find funding for art projects that don't have like a real massive economic viability to them. But we need people like that out there who are championing these things and supporting them, because it's hard work to do, and the artists who do it care about it a lot, and I think it's important work to support. So, yeah.
So from at least my perspective, from an executive producer standpoint, when we kind of look for IP and look at the tool sets that are out there right now, I actually really see the entire development model changing because of these tools. Now, this may not apply to big already tentpole IPs, but it's really hard in this day and age to get a unique IP to get traction. Everyone's in the reboot era, everyone's in the sequel era, everyone's in that generation. So, but now which I think is a game changer when UEFN came out, you have an opportunity to really test your IP with a captive audience and make money in the first 6 months to a year of your development and time, therefore helping fund all the other animation parts of it. So for me now, my whole, sometimes studios will spend millions of dollars on development of IP before they hit go, and then it goes into a next phase, and then you greenlight the tens of millions of dollars or $100 million, and it's a lot of money to gamble on. But what this is doing is it's completely changing the ecosystem to now where unique creators and people with unique ideas and their own IPs want to test it in the marketplace, create a captive audience and community, make money, so that you can continue on your journey. So this is a complete game changer for me, and it has changed the way I think about development. Like, UEFN is an integral part of developing new IPs, but what it's also doing is giving us more freedom, us as creators and IP, people that are looking for IP, more freedom to kind of explore the more quirky ideas. Like everyone hears the story. Squid Game took how many years to get going? But now with this ecosystem, it makes all those kind of leaps of faith a little bit more achievable, and opens it up to the world. And then also community feedback within the Fortnite community will just make your product better and help fund every single aspect of production, whether it's linear content or continuing on a UEFN story.
Awesome. I'm going to open it up now, just if anybody has any questions here of anyone on the panel. I believe that there is a microphone that is somewhere there also.
Get ready for 3, 2, let's go, 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 go. On your mark, get ready, set, go, 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 go. On that jump, that get up and go, 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 go. On your mark, you ready, go. show. 3, get ready. 4, 3, 2, let's go, 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 go. On your mark, get ready, set, go, 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 go. On that jump that, get up and go, 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 go. On your mark, you ready, yeah, go. show. 3, get ready. 4, 3, 2, let's go, 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 go. On your mark, get ready, set, go, 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 go. On that jump, that get up and go, 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 go. On your mark, you ready, yeah, go. get ready. 4, 3, 2, let's go, 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 go. On your mark, get ready, set, go, 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 go. On that jump, that get up and go, 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 go. On your mark, you ready, yeah, go. On your mark, get ready, set, go, 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 go. On that jump that, get up and go, 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 go. On your mark, you ready, yeah, go. show. 3, get ready. 4, 3, 2, let's go, 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 go. On your mark, get ready, set, go, 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 go. On that jump, that get up and go, 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 go. On your mark, you ready, yeah, go. show. 3, get ready. 4, 3, 2, let's go, 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 go. On your mark, get ready, set, go, 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 go. On that jump, that get up and go, 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 go. On your mark, you ready, yeah, go. the show. 3, get ready. 4, 3, 2, let's go, 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 go. On your mark, get ready, set, go, 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 go. On that jump, that get up and go, 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 go. On your mark, you ready, yeah, go.
You guys, come on, come on, come on. Okay, you might have noticed that I managed to make it so that the audience is also lit up, not just me. Who here has seen a presentation by me in person before? Let me see some hands up. So you know what's coming. You know what's coming. For the others, let me explain a bit. What I like to do before I do a presentation, I feel it helps, loosen up myself and you all also, is to take a selfie with the audience. It's a lot of fun. I'll post on Twitter. You can retweet and say like, oh, I was there. Oh, look at me. I'm the one sleeping. And it's a video. So we'll all say hi from and then New Orleans. And it'll go like this. I'll say 3, 2, 1, and then we'll all go hi from New Orleans. However, not that I don't trust you, but I think we should practice once before, because I'll only have one video and I want it to be great. So, are you ready? I'll say 3, 2, 1. You say hi from New Orleans. I want you to be happy. Put your hands up. Be very animated and make it loud, because I do compare all the conferences I go to. And at the end, I pick a best one. I'll make a compilation video. Hey, here are all the conferences, and I'll say, maybe New Orleans was by far the most enthusiastic. So I hope that's going to be you this year, because last year it was a bunch of Norwegian students in a half-full hall. So okay, let's practice. Are you ready? 3, 2, 1. was good. That was good. Good. So you were at like high from, I want to see high from all the way up. I think then we'll be able to do it. We'll be able to, because Unreal Fest, it's the fest. We'll be able to like, I want it to be number 1. So let me see if I can get, oh, I'm gonna have to scroll. Okay, is everyone ready? 3, 2, 1. Oh, wow, that was amazing. Thank you so much. I think actually a contender for first. Not kidding. Yeah. Welcome to Advanced Debugging in Unreal Engine. This presentation is packed, so I'm going to be talking quite fast. A little bit about me. I'm Arnbjörnsson. I'm an evangelist at Epic Games. I put all my stuff on my website, art.games. Okay, no time. So intro. Don't guess, don't assume, check it. You can debug both C++ and blueprints, take advantage of it, and also be curious, investigate, and find the cause. Usually when you fix a bug and you don't really know how you fixed it, but good enough, I would say spend a little bit extra time to figure out why was it, bugging out. Because usually you will learn something new, and it will make it so the next time you see this bug, you'll be even faster at fixing it. Also, some of you might go see this online and go, I don't want to watch this video. I just want, the stuff. Can't I see it in text format and, search through it and stuff like that? You can. When this presentation goes online, then this text compendium will follow it. So it's not for you in the audience, not yet. Just wait a few days. It'll be up on that link. I'm not going to teach you about making breakpoints, stepping in, stepping out, everything like that. However, I will tell you that you can also do it in blueprints. So there's the blueprint debugger. You can make breakpoints. You can see the stack. You can see what's variables and everything like that. Check it out. There's the QR code. Also, you might not know this, but you can automatically break on blueprint exceptions in the editor. So let's say you have a node. There's a no reference exception in blueprints, which is all managed. And you just get a warning, you're like, I don't know. So with this setting, it will automatically put as if you had a breakpoint there, and you'll see the stack and everything. I would actually recommend for most teams to just turn it on and check it into the project, make it default for everyone. Also, whenever you do get a blueprint error or warning that goes into the console, you can make it so that if you turn script stack on warnings equals true, you'll get the entire call stack instead of just the function that happened in. Really good and nice to know. Call in editor. This is like a quality of life one. You can enable call in editor for a blueprint event or function, and also for C++ there at the bottom, you function call in editor. And sure, of course, you can make it do cool stuff at edit time, but did you know you can also make it do cool stuff at runtime? So you can, for example, if you have 10 enemies, pause, click one of the enemies, and have a button that gives that specific enemies unlimited health or some inventory item or something like that. Print string, I know, I said in the description, oh, print string, lame, but it's okay. It's only print string is lame. You want to use print string and everything else also. So for example, there's the key property in the print string that allows you to replace a previous occurrence of that text on the screen if it exists. So here on the left side, I have XYZ that I'm spamming the screen, and other logs just kind of get swallowed up in it. On the right side, I'm giving them their own key, so they stay there, overwrite the previous one, and then other logs get their time in the spotlight. So the logs can be found in the /saved/logs folder. You can show even a log window in package build with a -log, so it'll show a little terminal window. This is only in development and debug builds, unless you want logs in shipping, which is actually what some studios do. You can use logging and shipping equals true in your target.cs file. And one thing that is quite neat is that you can change the runtime verbosity at any time with log name, and new verbosity. So my favorite ones out of these are log streaming verbose. What this does is that anytime an asset gets loaded in your game, whether it's packets or in the editor, it'll show up in the log. So it's really nice to figure out when something gets loaded, why something gets loaded. And also log garbage verbose when you are debugging garbage collector, because whenever garbage collector triggers, you'll see compacting hash tables, which is like one phase of the garbage collection, and it's the least like informal stat that you could get. I don't know why we have that. I think it should be hidden. I think, but yeah, if you want to see what every single phase of the garbage collector, how long it took, log garbage, verbose. Cooking, some of you are going to have your heads blown off now. So let's say we're cooking something, 5,000 assets, and then we're on asset number 2,000, and we get a warning or even an error. And it says, something went wrong, and it just, what went wrong? Like, in what asset? What asset was it? And Unreal just goes like, at you. So what you can do is, in the project settings, there's a cooker progress display mode. Usually, I would have just set the name and count, and then it would show you always before it starts cooking something which asset is cooking. So now if you get a warning, you know exactly which asset is in. But what I just figured out while making these slides is there's this new thing called instigators and names. So not only will it tell you what it is cooking, it will tell you why it is cooking that, why it got pulled into the build in the first place. Like here, we can see something happened in an old, unused blueprint that, oh, well, this isn't supposed to be cooked in the first place. Why could it get cooked? Hard dependency, maps, delete me old map. Oh, this should have been deleted. The widget reflector is an amazing tool if you're doing any sort of UI debugging. So with it, you can click that little pick hit testable widgets button, hover over it, click escape, and then it will show you the entire hierarchy. Like here we have an S border, we'll color it green. For debugging, you can click the source here. It's underlined. And if you click it, it will open Visual Studio, open the code. And because there's a bunch of borders in our entire screen, so which one is it gonna have a breakpoint on? Well, all of them. But we also have the memory address there, and there's this text there, CBP, conditional breakpoint. If you click that, it will copy the format that you should paste into a breakpoint to make it conditional. So there it will copy this equals cast to widget something, and then the memory address. So then put the breakpoint, paste that in there, and it will only break on that one specific object instance. There's the documentation for it and how you can open it. We have a team manager in Unreal Engine. It's built in, and it automatically gets disabled in shipping builds. It's teammanager.h, teammanager.cpp. Just check it out. It's quite cool. It's got a bunch of built-in functions. You should add your own. So you should extend it and add your own functions to it. You can force the team manager in shipping builds by adding the UI with team manager global define in your target CS file. You can also use the if with team manager to strip out cheat functions if you don't even want them compiled into your shipping builds. And I really like using the cheat manager with the execute specifier, exec, and also I like to override its console name with the override native name. So for example, let's say you have set player invulnerable function and give player inventory item, something like that. Then in the override native name, you can make them all start with player, and then when someone debugging the game writes in the console player dot, you'll see all the player cheats grouped together. And yeah, try to use it for your own cheats and debug functions so you don't accidentally ship it with your game. Something I have had happen with me. Who knew that? Okay, so like let's say a user buys a PS5 and puts a launch title in it and then connects a keyboard and starts hammering buttons. Who would? No, okay, I didn't know they would do that, but apparently, lesson learned. Debug camera, there is a built-in debug camera in Unreal for unpossessing the player and flying around. In it, you have all these, like I like to call it the what is this mode. Everything you look at will show you the full path to the actor if it has a collision on it. And it will show you the hit actor component, hit physical material, super nice. I will show you now a little example of using that alongside with other built-in debug functionalities before you decide that this is something you should build on your own. Just take advantage of the ones that are already built in. Let's say I have a game and someone just fixed a bug where if you shoot an enemy in the back, the game crashes. So now I need to reproduce that, shoot an enemy in the back. So let's start playing it. I'm already losing health, so I'm going to open the console and write God to enable God mode. Now they can't damage me. Also, I'm going to slow-mo 0.1 to go 10% speed. Now everything is super slow, I'm invulnerable, easy to debug. And now I'm going to teach you this new debug camera. I'm going to write toggle debug camera, press enter. It'll unpossess the player, and now it can fly around. Everything, like I look at, you'll see this little white line. That's going to be the normal of whatever you're looking at, in case that's useful to you. And now, I can fly somewhere completely different in the level let's say over a chasm or something like that. And I can just now open the console and write in teleport. Press enter, and now the player teleported there. Really, really good for all kinds of debugging. Now I can open the console and again write toggle debug camera. And let's say, oh, I want the game to be a little bit faster now, so I can yet again open the console, do slow-mo 0.7, and then shoot the enemy in the back. And yeah, seems like this has been fixed. So the debug camera, you can toggle it via keyboard with a single button. So it defaults to semicolon on keyboards that have it, like the USA keyboard. I think that's the only keyboard I know that has it. Like I'm from the Nordics, we don't have a semicolon key. We have a lot of like different weird keys. And they don't do anything in Unreal. So what I like to do is that I like to override globally in my documents, Unreal Engine config user input. By the way, you can override any config globally on your computer for both editor and packaged projects by putting into my documents. There I like to use the key Ö, so O with the 2 dots, because Ö doesn't do anything. So I do debug exec bindings equals key Ö, command toggle debug camera. Good use of or of course you can toggle it via console, toggle debug camera. And yeah, like I said, teleport console command to teleport the player character. I think you can even sometimes use insert, I can't remember. But yeah, support it, don't break it, because sometimes I've been part of projects where if a toggle debug camera it crashes immediately because there's some cast in the engine, not in the engine, in the game's code that always assumes that you're in the player's camera and not a debug camera. So yeah, if you do try it in your company's project and it breaks immediately, go to your programmer and tell them, hey, I told you you should support this and we shouldn't reinvent the wheel. Also, fun fact, you have a little toggle display there, with backspace key. It disables all HUD while in the debug camera. And it's really great for taking screenshots, and it's amazing for doing trailer footage. So I like to connect the controller in, turn off the HUD, put slow-mo on, and fly around with the smooth camera movement, and it's really nice. Visual Logger, I'm not going to talk much about it, because there's already an amazing talk from Rare from an Unreal Fest, can't remember what year. But with it, you can save as much data and visual data as you want for each frame of your application, and then play it back and visualize it like that. Check out the presentation. Here are some startup parameters for when you're starting your games, start directly from editor or even from Visual Studio, whether packaged or editor itself. Let's say you have a game that only crashes in the packaged folder, so not in Visual Studio, and it does it super early on, and you want to basically start it by having it wait until you attach to it. That's what wait for attach will do. It'll block the game until you attach with the debugger. However, that's so, last year. So what we have even better is that you can start a game from Visual Studio as if it was in another directory, using the pack files or IO store files, using the saved files, using everything. So like, for example, let's say you have a shipping game on Steam or any other store, and it's crashing. It only crashes like on the store, and you're like, no, how do I debug it? Just go into Visual Studio, put -basted, put the entire folder path to the Steam folder, to the Win64 folder, and then you can even, you don't have to do shipping. You just switch it to development or even debug game or something like that, and it will use the pack files. You don't have to cook everything again. You can just use the cook files somewhere else. I shipped a AAA game without knowing this. It's like, why don't we put it at the top of our documentation? Like, you might want to know this exists. So if this was already too much for you, like everything before, and you were nodding off, I need you to come back right now and look at this, basted. Okay. You can also override config values with -ini. So -ini and then :game, you can see the format there. Really, really good. So you don't have to constantly edit the ini files themselves, just override them like that. And also you can override CVARs with DP CVARs, stand for device profile, but you can use it for anything. Console commands, object is my favorite one, OBJ. So you can write, I say object, but I mean OBJ. You can write object list to see all objects in your game currently alive grouped by class, and they get sorted by the memory they take. But you can also do then object list class equals, and then put the class name that you got in the previous one, and then it will list every single object in your game of that class type. So basically now you have a way to see every single object in your game. You can also dump the properties of an object. So do object dump and then pass to the object. And then you get every single property. This is also good in package builds, really good. And then lastly, if you have an object that just isn't getting memory collected, and you don't know why, garbage collected, You can write object revs name, path to the object, and then shortest, and then it will list what is keeping the object from getting garbage collected. And a little extra tip there, you can write object GC to trigger a garbage collection. I want to demystify a little bit, clear things out for the Unreal build configurations, because we do have a little bit of misinformation out there. Some of it is because of us, sorry about that. So we have 4 build configurations for your code modules: debug, development, test, and shipping. And we have one pseudo called debug game that uses debug for game modules and development for engine modules. You might have heard from us or somewhere online that you cannot debug shipping builds. That is a lie. A shipping build is just as debuggable as any other build. Actually, fun fact, a development build and shipping build have the same amount of code optimization applied to it. Did you know that? It's quite cool. So debug, development, test, and shipping, I put debuggable in IDE for all of them. They're all debuggable. However, that misconception might have come from that we don't automatically stage the symbols. So when I say stage, I mean when you go into platforms, Windows, packets, and then you get your game packaged in a single folder. We will not copy the symbols over to that folder unless you explicitly enable it, and that's on purpose. We don't want you accidentally shipping the symbols. You're supposed to make a build and take the symbol. Well, anyways, I'm getting ahead of myself. So other differences between them all, the code is not optimized in debug. Otherwise, full optimization is on development, test, and shipping. Same amount of optimization. Console is enabled on everything except shipping. Cheap managers and everything except shipping. Inside Visual Logger and everything except shipping. And now it gets a little bit different with checks and ensures. We have slow and normal in debug. We only have normal in development. And then we have nothing in test and shipping. Logging is not enabled in test and shipping. And then lastly, debug drawing is not enabled in test and shipping. Whenever I say that something is not enabled, you can always force enable it per component. Just if you want the shipping with Cheap Manager, you can do it like that. If you want the shipping with logging, you can do that with those. Those goes into your target CS file. If it's all caps, it's a global define. Just add it to the global defines array. So you noticed I had a little asterisk there in code optimized. That's because you can unoptimize parts of it. So some of you might, for example, go, oh, I'm debugging. I can't see the like some functions are getting inlined and some variables are getting optimized away into registers. Let's just switch the entire project over to like debug game or debug. I think that's an overkill. Honestly, most of my debugging is in development. So what I recommend is for individual C++ files, you can make it so that only checked out files will not get optimized via the adaptive Unity build. So there's this property there called adaptive Unity disables optimizations equals true. I recommend you put it in your build configuration file because that is not checked into the entire project. Or you can put it in the target if you want to, it's your project. And then you only need to check out that file. You don't have to touch it, you don't have to save it, you don't have to do anything with it. Just check it out in perforce and then suddenly it's unoptimized. You can also do it per module like that, lots of text, and then you can do it for block of code with UE_disable optimization or enable optimization. If you do that, I recommend you have your continuous integration server fail if it catches that kind of code by adding the UE check disable optimizations equals 1 as a global define to only those builds. And if you really, really, really want to, for some reason, have some code go through unoptimized, you can add _shipping to those. So yes, like symbols, I said, always turn on the shipping symbols for all your Unreal projects, but also be aware of them. You turn them on in project settings, include debug files. Because if you ever make a build, and then you release it to users, and you didn't keep the symbol files, and now they're lost forever, you will never be able, like even if they send you their crash dumps, you won't be able to debug them. Even if you try to like debug something in it, you won't be able to. So it's very important. Don't ship them with your game, and remember that this is just for package stage builds. Visual Studio builds always make symbols. You can always debug those. So where are you supposed to put those symbols? I recommend in a symbol store / symbol server. There's documentation for that on Microsoft's side. With that, you can get access to every symbol for every build for debugging automatically. Visual Studio will just fetch it itself. And it can be, you can store it like on a shared folder, just on a NAS drive that is accessible for everyone in the office or using VPN. Or you can also even expose it to the internet using a very stupid plain HTTP server. And you can even add username and password to it, which I recommend if you have it external facing, which is great if you have contractors, for example, or code dev studios that you don't want to give access to your VPN. And how you use it is, first step, in your continuous integration server, or whatever you have, use simstore.exe to put the simple files into a proper file structure. We'll do it all for you. And then step 2, reference those simple stores in anyone using Visual Studio that wants to debug using the simples. Here you can see I have 2 examples. One is the top one is just shared drive, my studio NAS. And then the second one is how you would use it if you were using an HTTP server. Like here's like an intranet with a custom IP or something like that. So let's say, OK, I'm now working on the main branch, and there's a release build that was made 2 months ago, and suddenly I am required to debug that release build, or get a crash dump and I'm required to debug it. What do? Do I shelve all my changes, and do I then like check out the branch from what that build was made? Actually, no. With source indexing, what this allows you to do is that just keep everything that you have, and then you get, you attach to the process or to the crash dump. Visual Studio will automatically download the symbols, and from the symbols, it will see which version each code file was, and then it will automatically go to your version control and pull in the correct version of that code file. And you can be on whatever branch you want, and it will just always be right, even though the function doesn't technically exist anymore. And yeah, this is how you use it. Also, did you know that whenever you're starting your game, Unreal, from Visual Studio, it will load all the modules and all the symbols for all the modules, so you can, of course, make breakpoints and stuff. But there are over 500 modules in Unreal Engine. And loading all these symbols actually takes a while. We're not doing it multi-threaded. It's like sequentially. And honestly, do you need to load all these symbols all the time? I just tried this on Lyra. And just by reducing the symbols I load from the default 500 to just the 20 modules, I was like, OK, these are the 20 modules I debug ever. It went from 42.5 seconds to 27 seconds without. It was a huge time save. It cut my editor startup time in half. I tried it also on Fortnite, because I can. And that one went, we still got 20 seconds of savings. It went from 110 to 90 seconds. But for that, it's already big enough that, like, it's already long enough that you kind of context switching anyway. So yeah, you decide whether it's worth it or not, because you still, like, OK, for example, let's say, for breakpoints, you need to have the symbols. But what happens if you hit an ensure or an exception, and I don't have the symbols? Don't worry, Visual Studio will automatically load them. And if you are stuck on a breakpoint and part of the call stack is grayed out because you don't have the symbols, you can just double-click, and it will automatically load them. And also in the modules window in Visual Studio, at any point, you can just search for the module, right-click, and do always load automatically. I recommend you really get crashes, like the workflow, up and running for your project. I have a presentation already on that called Crashing with Style in Unreal Engine. Check it out. In this video, I teach you how to customize the crash reporter and also to aggregate the crashes via a third-party website. But there were a few things that I did not mention in that presentation that since then I'm going to add here. So first is generic crash context set game data. So this sets a key value pair of text that at any time if your game crashes, it will put those put everything in this dictionary into the crash file. So for example, current level the player's on, or the current mission, or anything else that you think would be relevant to a crash. You can also add, excuse me, you can also add additional crash files to a scope, so like a specific function, something like that. With UE add crash context scope, and it supports both binary files and text files. And I would even recommend, whenever you have a crash, save the save game also into the crash folder. You can do that. Check search add crash context scope in the engine. We do have one example how to use that. It's quite easy. And yeah, assertions, they do also create crash directories. You can turn it off, but why would you? Just submit those also. You want to fix it, right? Here's a little magic trick for you in Visual Studio. You can set the next statement at any time. So yeah, change the currently executing line by dragging the yellow arrow. You can also control-click the smaller arrow on the line, or you can right-click and set next statement, or you can Control-Shift plus F10. There's lots of ways to do this, so don't worry. It's not like you're not supposed to. And with this, what you can do is that you can redo some code if you didn't catch what happened the first time, or you can even skip exceptions by just going forward. I'll show you an example. Here, sorry about the small font. Here, there's a function called debug me. I really want to debug it, but I might be just a little bit too trigger happy on the F10 button. So I start clicking F10, F10. I'm supposed to step into it on F11. Right click, set next statement. Let's just do it anyways. There, F11, and now I'm inside the function. However, take into account that you are running the function twice. You're not going back in time, so the code does get run twice. Okay, let's continue. F10, F10, F10. Oh no, and an exception. Ah, the debug session is over, right? Wrong. You can drag that yellow arrow one down. Exception no more. Magic. One thing about that is that, there was a variable there called actor velocity that never happened because we skipped over it. It will have some junk data in it. Just take that into account. There's 000, but if it was in the shipping build, it would be like some junk data. This is really good, for example, when you have something that is already doing something weird. Like maybe it's already on the way to crashing or something, and you manage to just catch it in the debugger. Let's say debug me was a function that did something more than just a single log. Let's say it got together a lot of data and then put it into a list. And then you're like, oh no, I missed what it did. I need to go back and do it again. Maybe it's fine, because sure, it will put that data into the list again, and the list will be completely unusable, and the next line will probably crash even more severely. But you didn't care, because you just really needed to know, how did the crash happen in the first place? How did it gather the data? What was it doing? It's like summoning a corpse to come back to life to answer 5 questions, and every time it answers, a limb falls off, So it's that kind of debugging. You can watch for globals. This is something that took me a little while to figure out. So you can see globals in the watch list by using module name, exclamation mark, variable name, syntax. And here's 3 examples using config, plain editor context string, and frame counter. Config is just like everything it has loaded from ini files. And great if you got some ini files messing with you and you don't know why it's not pulling in the right values, you can see the final values there. Plain editor context string, someone told me about this, because sometimes when you do multi-window plain editor debugging, you want to know whether you're currently debugging the server window or the client window. And it will tell you there. In my case, it is just standalone, because I wasn't doing multi-window debugging. And frame counter is really nice if you're, for example, stepping through a lot of tick functions. You want to know everything that happened in a single frame. Then you can even right-click and make a data breakpoint there. And then you'll get a little exclamation mark as soon as you go into the next frame. Quality of life. When you're going into the data tips, you hover over a variable and you go deeper and deeper and deeper, and then you accidentally just move your mouse a little bit too far, and the whole thing disappears, and then you turn into left Ari, being very, very disappointed with yourself, and what are you doing with your life? Well, Ari on the right, he found a property called keep expanded data tips open until clicked away. And he enabled it, and look at how happy he is. He can expand all the data tips, and then he can move the mouse wherever he wants to, and nothing happens to it. Happy Ari, happy developer. If you need to run away now to enable this on your computer, I would understand. Okay, let's say now you are paused in a debugger in Visual Studio, and you want to know, let's say, some blueprint function called this. And you're like, oh, well, let's see what the blueprint call stack is. So you check the call stack, and it just says, there's 10 functions that just say blueprint land. Someone in blueprint land somewhere, I don't know. And if you want to know, you can just write into the immediate window, print script call stack in the core module, and it will print out the entire blueprint call stack. What I like to do is, because this is a lot of text, and I can't remember that, so I open the command window, which is a different window, and I create an alias BP, you can call it whatever, I called it BP, evaluate, eval, unrelated core, print script call stack, and now, in the immediate window, I can just write greater than BP, and then we'll print the blueprint call stack. When you create this alias, it will remember it, so you only have to do it once. Oh, and one extra thing. In monolithic builds, you don't need the module, because there are no modules in monolithic builds. Okay, conditional breakpoints. Some of you are going to go like, oh, that's how you do it. Because that was how I was when I figured out how to do this. While I was making this presentation, I've been working, I've shipped a AAA game. I worked at Epic Games for over 2 years, and I just recently learned that you can do this. So, conditional breakpoints for F strings, that's how you do it. Conditional breakpoints for F names, it's a soup of characters, but you can do it. Or You know what we do at Epic? Do you know what most AAA devs do? They just edit the source code, even engine code. They just put like, whatever, if fnum is that, then UE debug break. That's usually easiest. But sometimes maybe you don't have the ability to be able to change the code or something like that, then sure. Also, don't take a picture of this and try to like, transcribe it. When this presentation goes online, then this link will work and you can just copy it from there. Remote debugging, let's say you have an artist or designer or something and they have a bug and you really want to debug it, but they don't have Visual Studio on their computer. What you can do is you can just tell them to open up msvsmon.exe. There's something free they can download from Microsoft. And it's a portable executable, meaning that you only need that executable itself and nothing else. So you can put it on a shared drive, you can check it into your source control and tell them to just double click that. This upper window will pop up saying accepting connections. And then on your computer, where you have Visual Studio, when you do attach to process, in the connection target, you put the computer name. And then you'll see the processes on their computer and you'll be able to connect to it. Wouldn't it be nice if we'd be able to debug crashed processes before they crash? You can. So if you turn on a prompt for remote debug, then at any time before Unreal crashes, it will show this pop-up. I'm about to crash. Do you want to have someone remote debug this crash? And if you click yes, it will like continue, because right now it's just a model dialog, it's freezing everything, and programmer can't do any stepping. And if you click no, it will just open the crash reporter like normal. Oh, live share. I don't know how many of you have ever tried live share. I know it's in Visual Studio because it's got that button in the upper right corner. I recommend you try it out. I tried it and I was just immediately like, I need to tell the world about this. So with this, you can pair program or debug with a single click. You can look at different files and even different frames of the stack from each other while debugging. And you can live collaborate with up to 30 people. This is insanely powerful. You're definitely missing out if you never used it. And I'll show you an example. Let's say I'm Ari, let's say, hypothetically, and I am having trouble debugging this. I'm like, oh, I don't know how to debug this, oh my God. And then my lead is trying to tell me through a Zoom call, like, no, hover over that variable. No, not the other one. Oh, you're an idiot. And I'm like, yeah, I know. So then I can just, use live share. So now I just use that little live button there that has prime real estate, click it. Wait a second, and it'll say, you have now started this live sharing session, and I've copied the link to the clipboard. That's all they need to do. Idiot proof, Ari proof. And now I can send this to my lead. Here you go. And what's cool about this is that the lead, the lead doesn't even have to have Visual Studio on the computer, because if he clicks the link, it will open Visual Studio Code in the browser, and it will download the code file that I had open, and it will show the stack and everything. So your lead can be like on a holiday in Bahamas, like with a tiny little air book, and then you're like, help debugging. And they're like, I guess this is possible. And if they don't want to use Visual Studio Code, there's a button, and it will open Visual Studio like that. And I can see that I'm connected there in the upper right corner. I can see the idiot Ari, everything he's doing, because like he's moving the mouse around and selecting text, and it's like Google Docs, you can see it there. And I'm like, you're in the wrong file. I'm going to go down the stack. Anywhere in the stack. It doesn't have to be where Ari is. And I'm going to look at the properties. It will show the data tips and everything. It's all coming over the wire. And then I can go like, oh, OK, I see it here. Now I can summon Ari. I can click that little join and click focus. And now Ari will get summoned to where I am. He's like, oh, there it is. I understand now. This is really cool. So because you can create your own watches. You can go anywhere in the call stack that the host, in a different place than the host is. And also, remember, up to 30 people can do this. So let's say you're a lone developer late at night, and you're like, oh, it happened. The bug happened. The elusive bug that only happens when there's a blue moon and a virgin has been sacrificed. It happened. And you just copy that link, and you send it into the coders channel, and you say, everyone attack it. And then suddenly there's an orgy of 30 programmers coming all with their fingers in the call stack. It's really cool. It's a really nice feature. Okay? Yeah. We have multi-process debugging also. In Visual Studio, and with it you can attach multiple processes and put a breakpoint, and whichever process hits the breakpoint first will just hit it. And one thing that's really cool, let's, for example, say that you're trying to debug shader compiler worker, and you're like, oh no, shader compiler worker crashed. How do I debug that? Because it's like launched as a process of an Unreal build. Well, there's this tool called Microsoft Child Process Debugging Power Tool. What this allows you to do is automatically attach to any child process. So yeah, just easy peasy. Also a little bit about multi-thread debugging. Did you know that whenever you are debugging and you step through a single line, you just press F10, step to the next line, every other thread in your application runs a little bit, just a little bit. It's like a game of green light, red light, you know? You are, in the time it takes you to press F10 and it goes from one line to the other, the computer goes green light and all the threads go like, oh, and then red light, oh. It makes it really hard to debug, especially if many threads are going into the same function, because then another thread could hit the same breakpoint before you've been to the next line, which is really weird. And then you're actively stepping to the next line for multiple threads, and your execution pointer is like going up and down and up and down, and you're like, what is happening? Visual Studio is having a stroke. No, your threads are. So what I recommend is open the threads window, select every single thread except the one you're debugging, right-click, and freeze them. You can also do thread-based conditional breakpoints, just filter by thread name equals game thread. And you can use the actual names of the threads. You don't need to use the IDs. Quickly about Unreal VS. It's a plugin, comes with Unreal. It's on your computer already. Just double-click it, install it. It allows you to set starter parameters directly from Visual Studio. And it remembers the last few ones. Really nice. We have a NatWiz file format. It's, we make our own called Unreal.NatWiz. You can see how we do it for inspiration. Sometimes you might want something custom for yourself. You can just put it into your My Documents file, call it something.natwiz, and if you modify it in Visual Studio, it will instantly update in the debugger. So now you're thinking, why should I create my own NatWiz file? Well, here's an example. Look at the first picture there in the middle. It says before. On level added to world. You hover over it, and it'll just say persistent level. And you're like, well, duh. What am I supposed to do with that? Which persistent level? Well, what I like to do is that I put a visualizer for uLevel, like this, and display string is name private, and then the outer private name. And then it will show me persistent level dash beam walkway. So you can do stuff like that. Also, if you have an array of 100 items, you don't want to expand every single one, you can make the type that is in these arrays to just have one property that you're searching for in the parent name, so you'll just see that on the surface, if that makes sense. Visual Studio does have now this blueprint support, so you can see in which blueprint some new properties were changed. However, take into account that this was originally in Rider, and they're the OG for that feature. And actually, you know what? Visual Studio, Rider, Visual Assist X, they all have different ways of working better with Unreal. I recommend you check all of them out and choose your favorite. Wouldn't it be nice if you could debug shaders? You can. What does it mean? You can debug shaders, like a single pixel, and go through every single, you can step through it, like code. So here's an example. Let's say if you watch my last year's presentation called Maximizing Your Game's Performance in Unreal Engine, you should check it out. It's on my website, ara.games, check it. We had this one material that had 3 noise functions. Let's say for 1 pixel or 2, it was black or something like that. I just want to see exactly what's happening, so I want to debug the shader. So here I have it already working. So this is the material. Now I go over to RenderDoc, for example. There's the draw call. I'm going to select a pixel that I want to debug, and then just click the debug button. And now what I can do is I can step over functions. I can step into functions. And weirdly enough, you can step backwards also. If you go too far, let's just step backwards a little bit, because it's like simulated. And if you step far enough, there you can see. That's the material code that I just showed you, 3 noise functions. And you can step into them. You can hover over the variable to see the value, like that. Which function is it? Oh, it's function number 3. OK. There's a position. See everything. This is quite cool. I knew that this was possible somehow, so I thought I'd figure it out before this talk. How to do it? You edit the console variables.ini file. There's our documentation on it on unrealengine.com. And you uncomment these lines. Shaders that optimize equals 0, but that's only when debugging, not when profiling. Shader symbols equals 1, that's the important one. skip compression equals 1, and then optionally you can do shader development mode equals 1. That's good if you are hand editing your own shader files or Unreal shader files, because it'll then give more details in the output. For package builds, disable IOStore, because IOStore doesn't know how to bring the shader debug files over. Maybe the IOStore team is watching this and they'll fix it. Also, if you're using the EOS overlay, you should disable that one, because RenderDoc and EOS overlay use the same hooks, and there'll be a little conflict. If the EOS team is watching it, maybe that's something we should fix. And then in PIX, it's quite easy. You just start the process from PIX. You can use the dash attach PIX launch parameter, and then you just make a GPU capture. I use RenderDoc for this demo. And currently, it only supports DirectX 11 shader debugging. You can force your Unreal game to start with DirectX with the dash DX11 launch parameter if it has support for it. And then you just start the process from RenderDoc, with dash RenderDoc dash DX11. This is a little extra slide. I know it's not debugging, it's profiling, I know. But I thought it was so cool, I couldn't not have it. So you can actually, let's say you have, you're profiling a frame, and I think one of the draw calls is quite slow, and you're like, okay, I should optimize it. But what should I optimize? What part of that draw call is slow? So you can use the profiling software of your graphics hardware. In my case, I had an NVIDIA graphics card, so I downloaded Nsight Graphics. AMD and the consoles will probably have their own. I didn't check it out because this was quite last minute. And with it, like this is from a package build. I tested it. And it will show you here, per function, what was the slowest function. Here, there's highlighted material expression noise, taking 95% of the frame time. And if you look there, for every line in the shader that is not a function call, that is just an actual instruction, it will show you how long it took out of the entire draw call time. This is really powerful, really cool. Just know that you can do it. So when I was making this, I asked the Twitter community for a lot of help, and they definitely came through for me. I recommend that you check out the thread. There's the QR code. There's a bunch more of hidden debug knowledge that they were all calling out that you should definitely check out. I want to just thank the entire Twitter thread for your help. Here's just something that I could fit into the slide, and everyone else that I couldn't fit here. Apparently, I thought I would be over time, but I practiced this so much, and I was so efficient that we have 5 minutes for questions. Thank you very much. Still have 5 minutes, right? Yeah, there's supposed to be a microphone in the middle of the room.
2, 2, 1, 2, hey, 2, 1, 1, 2, hey, 2, 1, 1, 2, 3, hey, 2, 1. Two, hey, 2, 1, 2, hey, 2, 1. Yep.
1 for the money, 2 for the show, 3 get ready, 4 3
one.
Let's go, 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 go. On your mark, get ready, set, go,
one.
go, go,
Two,
go.
one.
On that jump, that get up and go, 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 go. On your mark, you ready, yeah, go.
Hey, 2, 1, 2, 2, 1. Hey, 2, 1. Two, hey, 2, 2, 1. Hey, 2, 1. Hey, 2, 1, 2, 2, 1. Hey, 2, 1. 2, 2, hey, 2, 1.
show. 3, get ready. 4, 3, 2, let's go, 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 go. On your mark, get ready, set, go, 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 go. On that jump, that get up and go, 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 go. On your mark, you ready, yeah, go. the show. 3, get ready. 4, 3, 2, let's go. Go, go, go. On your mark, get ready, set, go. Go, go, go. On that jump that, get up and go. Go, go, go. On your mark, you ready, go.
Hello, Wow, I feel like a rock star. Hope I don't turn it into a comedy. Anyway, well, welcome to our session on the rendering roadmap. My name is Michal Valient. I'm a senior director on the Unreal Engine team. My areas are rendering platforms, some online, and foundational low-level systems, cooking, iterations, etc., etc. I'm going to be joined by Kevin, who is a lead rendering programmer, and Mihnea Balta, who is our engineering director. Kevin is representing our graphic features team. You know, they're working on all those features contributing to the shiny pixels like Lumen, Nanite, and so on. Mihnea, on the other hand, is leading the rendering architecture teams that build all the underlying infrastructure, parallelization, shader compilation, you know, things that make it all fast. So I'm going to start with the overview of the roadmap, and they take over with some more details. So it's been, what, about a year and a half since we introduced UE5. We brought a lot of next generation technologies in that clearly redefined what we think about games and what's possible. Nanite, Lumen, virtual shadow maps, temporal super resolutions, other innovative areas. We've been gradually battle testing these features on our company projects. You might have seen some of our public-facing demos. And of course, last year, we introduced all of this into Fortnite Chapter 4 on PC and consoles at 60 FPS. That was a lot of fun for the team, I can tell you that. So we're pretty happy with how the tech evolved and matured between 5.0 and 5.3. But of course, there is a lot more work to be done for us. So, you know, what's next? I hope by now you've seen our roadmap. It's online, and it now contains the future-looking forward area. These are all the things we are ready to talk about. And there are, of course, more things that we are still considering, and we'll be updating this going forward. And we've been looking at how to frame this, because we cannot just go ahead and say, well, we'll do more of everything and just leave. So we sort of found like a few areas: more data, more pixels, more fidelity, and more speed. So why more data? Well, the simple truth is that the scenes we are seeing, the scenes you're making, are just getting massive. Everyone wants to use thousands of actors, millions of instances, and the worlds are getting larger and larger. With Nanite, we changed what we think about geometry detail, and recently we enabled it with foliage. So that's fun. On another axis, our shaders are getting more and more complex. We are using layers upon layers of extreme high fidelity textures. When you think about our characters, they're getting more realistic. Everyone wants to use a lot of them on screens. And with that, for example, the complexity of just hair and grooms is growing significantly. So unfortunately, with all of that data explosion, the GPUs didn't really keep up, especially when it comes to memory. It didn't grow as much as we'd want to. So we really need to rely on virtualization in a lot of our efforts. Nanite, of course, is a virtualized geometry system that allows us to render tens of millions of triangles in a fixed memory budget. It also changed the way we think about asset creation, because you no longer have to think about LODs and store them on disk. So that actually reduces the data. And going forward with Nanite, we, of course, are working on optimization, but also introducing tessellation, which allows us to amplify more and more of this data without, you know, breaking the bank when it comes to disk sizes. Similarly, virtual shadow maps is sort of a must when it comes to Nanite, because it's the only way to get pixel-precise shadows to show all that intricate detail that, that you get in a scene. Virtual textures, another angle to this, allows us to stream only the tiny bits of texture data that we really need to render the scene, instead of all the MIPS or just, you know, individual MIPS. So Again, working in a fixed memory is a key, and we are looking at how to enable this by default in all the projects. We are having an ongoing work when it comes to large word coordinates, of course, to fit all of that content into exponentially larger environments. And going back to the characters, hair and groom system is getting an update so that you can create scalable and very detailed grooms with less effort. There is a slightly invisible aspect to the data that is so invisible I don't even have it on screen. It's a lot of the engine work coming in things like compression, better data structures, how to express millions of instances without hundreds of megabytes of data. World partition streaming allows us to stream only things that are really around you and relevant to what you see on screen. Procedural generation of content allows you to create vast worlds without hand-tuning everything. Virtual assets help during iteration times and development because you don't have to pull the whole project and gigabytes of data from Perforce. You only get the relevant pieces. So hopefully you've seen some of these being mentioned in other talks throughout the Unreal Fest, and if not, I'm sure they will be online. More pixels. So this goes hand in hand with more data. It's sort of runtime representation of the same problem or same challenge. 4K became a standard when it comes to consoles. PCs and these gigantic monitors are basically swiftly pushing past that. And despite that, getting to 4K is just not easy. Our render passes are much more complex, shaders are heavy, so the cost per pixel actually increased, and we need to get smart about it. There are few classes of algorithms in which we are investing to sort of get the best bang for the buck. Temporal super resolution is one of them. It's a cornerstone of our rendering pipeline. It allows us to upscale so we can generate those 4K images at a fraction of their original cost, and we are making it better and faster. We are also researching nanite variable rate shading that allows us to shade certain portions of an image at a lower rate and further reducing the overall cost. And we do all of that so that we can stuff more stuff on screen, so we get more detail. I was just looking back at the graphics progress, and it's sort of funny that we are still chasing this dream of photorealism and trying to get all these beautiful materials and best lighting, all the physical phenomena, water, smoke, fire, and do that all in fraction of a millisecond instead of hours that it takes to offline render. And we're still not there, but I think we're getting close. I have stylized rendering on the screen, but that's sort of to just emphasize that it doesn't make the problem simpler. It's actually interesting because it benefits from all the same technologies as photorealistic rendering. If you look at Fortnite, a heavily stylized game, how beautiful it is with lumen and nanites and all the detail, I think you know what I mean. So when it comes to more fidelity, of course, lumen, we are continuously evolving it and making it better at 60 FPS. We are heavily investing in our ray tracing architecture, especially on the consoles. We're looking at things like how to more efficiently ray trace nanite and make it something that people can use. On a shading front, we have Substrate, which is our new material system and allows us to express very complex materials, and it's a major step towards the parity with these offline renderers, of course. We are investing in volumetrics, both in real time, coming from Niagara, but also offline, created from whatever content creation package you like and import it through VDB. And of course, we are continuing to invest in our path tracing, which is sort of a ground truth for all of our algorithms, but it also has seen an uptake when it comes to non-game usage, pre-rendered cutscenes, linear content, architectural visualization, and so on. So the last bit, performance, it's sort of implicit, all the features that I mentioned, they have this component of more and more performance. And we simply have to do it just to get some new features on screen, because they also need a piece of that budget. And it's getting more complex. 60 FPS is a baseline standard people expect. Some games are pushing even further. So there is a lot of work to do. And sometimes this is just about designing for more cores. Sometimes it is just optimizing shaders. But a lot of the time for us, it's about creating an algorithm and options that allow you to sort of balance the quality and performance that works for a project. Lumen and virtual shadow maps are a great example of that. So with that in mind, there's still a bunch of focused areas we're going to talk about later that we push to get the most of the performance. Of course, we are focusing on all the modern APIs to claw every bit of the performance possible. We are expanding our usage of asynchronous compute to keep the GPUs busy. And one of the new features we are working on is bind less, so that we can move more and more of the processing that is traditionally done on a CPU to the GPU, more towards GPU-driven rendering. On the CPU side, we're working on parallelization to reduce the wall time of the rendering. Lastly, not all speed is about faster frames. For rendering team, it means mostly things like reducing shader compilation time, making sure that we only compile the shaders that have really changed, and of course, just reducing the number of permutations. So, hopefully, next year if you meet, there will be no meme on the internet about like tens of thousands of shaders being compiled in Unreal when you start the editor. So, that's it from me, and with that, I'm going to hand it over to Kevin.
Thank you. All right, hey everybody, I'm Kevin, and on behalf of our amazing graphics teams, I'll be going over some of our active work and some future-looking items. So there's a lot to go through here, so I'll keep it fairly high level. Let's start with nanites, our virtualized geometry system. And yes, those are triangles. First up, we have dynamic tessellation. This is a runtime mesh amplification and displacement technique. You might be familiar with the concept since we had support for hardware tessellation in UE4 on some platforms. That was removed in UE5, and this tech is here to fill that gap. Now, you might have made the observation that nanite can already render extremely dense meshes all the way down to small-scale detailed geometry. And while that is true, it can take a lot of disk space to store all that geometry, and all the detail is pre-baked. So one use case this enables is details and procedural displacement textures. So for example, to add fine detail to your nanite landscape mesh, like in this example here to the right. Another use case is to use lower poly meshes and up-res them using this tech for significantly reduced disk space at the cost of runtime performance. So this is a native implementation in the nanite pipeline. So we get built-in support for all nanite platforms, regardless of hardware. As another example, here's a simple low-poly sphere mesh with a megascan texture applied, including displacement, in comparison to the base mesh. And just to mention the user experience side, the workflow will be very familiar to those working with materials. So the prototype work in progress for this is in our mainline branch already, and we are actively battle testing this and exploring best practices and use cases for experimental release in 5.4. So next up is our optimized shading effort. This is major foundational work to allow more flexibility when evaluating nanite materials. The gist of it is that we can evaluate material shading and compute shaders instead of pixel shaders. And some of the benefits this enables is variable rate shading, where you shade samples at a reduced rate where the frequency isn't needed. Seen on the screenshot here is a visualization of the shading rates, and as you can see, the majority of the samples can be shaded at a reduced rate, leading to significant shading speedups. Another benefit is the ability to address empty draws. So in the current pipeline, there's a possibility that we end up generating a good amount of draw calls that don't end up affecting the output, but they still add performance overhead by keeping the GPU idle. So with this new system, we can eliminate that problem. We're currently targeting 5.4 for this technology, and there will be a detailed technical talk in the future here, so stay tuned for that. Final nanite feature I'll talk about is spline meshes. So experimental in 5.3, we have shipped native support for nanite spline meshes. So you can take a spline mesh material and assign it to a nanite mesh, and it will work as expected. Spline meshes are often used for large world features such as roads, rails, or curved walls, and enabling nanite support will run these meshes through our virtual shadow map FastPath together with other nanite content for more optimized performance. The plan is to move this out of experimental already in 5.4 and have it enabled by default. In fact, that's already the case in our mainline branch. And while this feature is fully fleshed out, it's still worth mentioning one item of future work here, which is instant spline meshes for further improvements to performance. So looking ahead, there are a number of items which we either have in research or on our wish list for the future. This is not a final list by any means, but covers some of the topics that we are actively discussing and we've heard community feedback and requests about. It's to be determined when and how we land these items, but we will be sure to let you know when the time comes. So you might know that things like ray tracing and foliage already work with nanites, but might not be taking the most optimal approach. So we're thinking outside the box to find suitable solutions and systems to tackle these. So the overall goal for the future of nanite is what we call nanite everything, which essentially means that we want to complete the feature matrix for nanites and have a solid workflow out of the box with no particular edge cases to worry about. So on to our next topic here, Lumen, our real-time dynamic global illumination system. So while Lumen is fairly mature at this point and works well out of the box with a lot of content, there are still a number of items we'd like to look at for the future. So one big item here is performance using Lumen with hardware ray tracing. Hardware ray tracing has benefits over the distance field software tracing path, but comes at a cost. Something we will be looking at is how to make Lumen with hardware ray tracing feasible for 60 FPS titles on consoles in the long run. This also aligns well with our general goals of improving ray tracing performance to target 60 FPS titles. And this goes hand in hand with our goals for using hardware ray tracing with shadows and nanites. So our main performance problem right now isn't actually the tracing of the rays, but the updating of the acceleration structures. With a lot of content being dynamic and with an ever-increasing object count, it becomes expensive to carry over all those updates that happen on the CPU to the GPU. So our main overall item for improvement here is to optimize the acceleration structure setup. And a few other future-looking items on our wish list are higher quality reflections, emissive explicit sampling for less noise, and scaling Lumen for even higher-end use cases. So as a final note, if you're using Lumen, and you should, I highly recommend you to take a look at the Lumen performance guide in our official documentation. It covers all the use cases and how to deal with scalability settings. So for shadows, in 5.0, we launched our virtual shadow map technology that has significant performance and quality benefits compared to the traditional cascaded shadow map tech, particularly when it comes to using nanites. So over the past few versions, we have worked on improving general performance for a wider range of use cases. But what we have found from licensee feedback is that it's still hard to tweak and optimize virtual shadow maps for certain performance problems. And this comes down to the fact that virtual shadow maps are performing well with nanites, but has some performance problems with non-nanite content, of which a lot of projects rely on heavily since we don't support nanite on everything right now. So what we will focus on going forward is the ease of use of VSMs, and some of this has already been submitted, and other things are being worked on targeting 5.4. A notable mention here is fixed budgets, something that we've seen a lot of requests for, both memory and performance. So something that's coming in 5.4 is shadow resolution auto-scaling based on the page pool memory limit. So instead of having to set a high memory budget for the worst case, you can now set a reasonable limit and let the system reduce shadow resolution when that limit is reached. So something similar for performance is also something we will be looking at in the future. On top of this, we are revisiting the default settings we have for scalability to get a better experience out of the box, in addition to adding new visualizations to let users better understand what might be expensive and where tweaks need to be applied. Finally, we'll be taking a look at our documentation and spend some time writing up performance guidelines to give users good examples of best practices to go for. We've also introduced a new performance optimization in 5.3, multiple actually, like better distance light handling when you have multiple shadow casting local lights far away. Additionally, we've added better caching persistence to avoid re-rendering objects that were recently cached around the camera. And in 5.4, we are aiming to introduce a new hierarchical instance culling system that accelerates having more dynamic shadow casting lights in the scene. So longer term, we want to look at improving ray trace shadows. There are a number of challenges here, similar to nanites with tracing high-res meshes and using the limited ray budget we have on current-gen hardware. The good thing is that ray trace shadows will benefit from the acceleration structure improvements I mentioned earlier. Another long-term goal is to allow for more shadow casting lights. Shadow casting local lights is a typical expensive part of a scene, and often the solution is to simply limit the number of shadow casting lights, which might be a limitation for building a complex scene. So something we are researching here is the possibility to use stochastic light sampling in an attempt to achieve more or less a constant budget, many light solution. So this will be based on hardware ray tracing and does have some common ground with ray trace shadows, so we will look at how this all plays together. But while this is in early research, we are still committed to the long-term goal of supporting many shadow casting lights, no matter the approach we take. The last point here is an overall goal we've had for a while, and that is to reduce the number of bespoke shadow techniques and integrate more of them into a coherent stack. We have something like 20 plus shadow techniques and concepts in the engine, anything from capsule shadows to per object inset shadows or distance field shadows. Vultr shadow maps cover many of them, but not all. So we'd like to have a more comprehensible shadow tech stack and where techniques complement each other and share data and caching structures where applicable. So in path tracing, we have added initial support for our new material framework substrate in 5.3 to be able to properly trace all the new features and more expressive materials. There's more to do here, and we'll continue on this going forward to have full support eventually. And to improve performance and achieve faster convergence, we have adaptive sampling coming as experimental in 5.4. The idea is to allow parts of the frame that have already converged to stop sending additional rays while noisier parts receive more samples. For artists, this means being able to leave the sample count relatively high and rely on early termination by an error threshold instead. So the bottom image here shows a sample heat map for the bedroom interior. And you can see the areas around the lamps receive more samples as these contain an emissive light bulb, which is not important sample directly. So we are also researching machine learning-based denoising, mainly targeting offline content, but while looking at existing methods out there, we've noticed some issues with temporal stability and are investigating solutions for that. So temporal super resolution, or TSR, is our built-in and well-integrated multi-platform temporal upscaler. Since this is first-party tech, it works well across our rendering pipeline, and we provide continuous performance and quality improvements to it. It's also easy to use, as is evident from when we enabled this in Fortnite Chapter 4 and only had to change one single material to make it all work. Another thing to note is that it's self-contained and easy to pick changes between engine versions. So we consider it production ready and highly recommend using it if you are considering a temporal upscaler for your project. I suggest taking a look at our extensive online documentation for details on how to best apply this to your project and scalability settings. So coming up in 5.4 is improved visualization modes for users to better understand what is going on in their frame. Furthermore, we have improvements to the algorithm itself coming in 5.4 to improve temporal stability in complex scenes. So by resurrecting samples from even older frames, we can do more informed decisions based on data that was previously occluded. This improves the upsampling for scenes where there are more moving things and greater depth complexities. And this is something we've already optimized and is ready to be used in 60 FPS console titles within a 2 millisecond TSR budget. And by popular request, we have moved the anti-flickering heuristic option into a material option to allow for better support for animating materials, like texture panning. So in research, we are looking into various ways to improve quality and performance. As with any temporal technique, we rely on information from previous frames and have to determine what pixel changes are valid or not. Here, we are researching ways to separate the underlying objects and features from, for example, lighting changes to improve the texture detail in dynamically lit scenes. Another future-looking goal we have is to optimize TSR to the point where we can enable it by default for medium scalability settings. All right, let's cover how we deal with our 64-bit CPU types on the GPU. So in 5.0, we switched out many of our 32-bit types to 64 bits to remove the precision constraints across the board to allow for authoring large worlds without special types or edge cases. This was easy enough to do on the CPU, but we had to think twice about how to deal with this on the GPU. So since native 64-bit types are either unsupported or slow on GPUs, the initial implementation in shaders was a simple dual float type. This would represent a tile and an offset to extend our range by tiling the current precision across the world. So this made it possible to extend the world bounds to 88 million kilometers, which is a fair bit larger than our old world bounds of 20 kilometers. However, we were unhappy with the precision this gave us, and we started working on an improved representation. So the new representation that we are experimenting with is similar to the old one in that it's also based on a dual float representation, but it's instead based on a low, high bit scheme to emulate a higher precision type. So this comes with an accompanying math library to be able to operate on this type with low error metrics. It gains us actually higher precision, even within the old world bounds, and it also allows us to balance precision versus cost by mixing and matching the old and the new. This work is underway for 5.4 and should improve many of the reported cases we've seen with imprecisions. So here's an example of some test content of a flight simulator flying at around 350,000 kilometers from the origin, which is a distance roughly equivalent to flying around on the moon. And as you can see in the top example, the attached cockpit components suffer from jittering issues, while the new representation doesn't. As a reference point, this would practically not even render in UE4. So this would also benefit use cases that want to go really small scale or cases that want to move really slow, cases that essentially needs that extra precision. So there are still a lot of remaining improvements to be made in this area, in particular to memory and systems that don't fully take advantage of this tech yet. We also want to take a look at improving the material editor experience to make it easier for users to author their materials in a more optimized space, rather than doing everything in world space. Now onto Substrate, our new material shading framework. At a high level, Substrate enables more expressive and correct materials by layering BSDFs through a common matter interface we call slab. The idea is to move away from the limitation of the fixed G buffer and open up new opportunities. So here's a basic layered material with anisotropic carbon fiber as a base, layered with a colored coat and finally a dust layer. And some of the benefits of Substrate are pay for what you use. No longer a fixed packed G buffer where different shading models have different encodings and fight for space. The material buffer allows for each pixel to build up the data it needs. And scalability is at the core of this system. It's possible to automatically collapse the substrate layers down to simple parameter blending, and this can be defined per platform. So in the example here, you can see a complex layered material to the left that takes 72 bytes per pixel and evaluates multiple layers. And to the right, it's the same material scaled down by automatic parameter blending to the point where the material takes only 12 bytes per pixel and is represented by a single layer. So the look will differ slightly, as you can see, but it's because it's removing features. But it's a great tool to automatically control cost and complexity. Substrate adds a great number of advanced features that aren't possible with the old system. Complex visual features like glints, rough refractions, specular lookup table, proper horizontal blending between conductive and dielectrics, and many more. Note that some of these advanced features are on the expensive side and might not be feasible to use extensively in a game today. But the idea is that we don't want to artificially limit ourselves, since this is a generational upgrade. And the scalability of Substrate ensures that you can pick the features you want and only pay for those accordingly. So this is live in experimental since 5.2. It requires you to enable it for your project, and it will auto-convert your existing materials to matching versions in Substrate. It's fine to experiment with, but don't go out there and enable this for your production projects quite yet. You can find all the technical details in our recent SIGGRAPH talk, and we are aiming towards production ready in 2024 by focusing on user experience improvements, performance parity with existing fixed shading models, full platform support, and further improvements to auto-conversion of legacy materials. So we have some new ongoing efforts to improve volumetric content workflows and visuals. So in collaboration with the Niagara team, we're developing a new component for rendering heterogeneous volumes that support proper shading and things like the path tracer. So to operate on volumetric content, we are developing a new native asset type called sparse volume textures that is efficient to keep in memory with support for streaming and arbitrary sampling from shaders for real-time rendering. This asset type is populated by importing VDB files and supports animations. This was released as experimental in 5.3. And if you want to know more about this feature, we have a talk coming up after this in room 238 that covers this in detail. And here's a little bit of a teaser for that talk. It's a video of a path-traced heterogeneous volume using sparse volume textures. Lastly, on volumetrics, I want to mention some new tech that is being developed, local fog volumes. We've heard feedback on the difficulties of populating worlds with impactful and contextual fog that can be authored to fit the scene. So we've set out to develop a new component for placing local fog volumes that can be authored to fit your particular location in your scene. It's currently being developed with low-end platforms in mind to make sure that it can be used across the board, something that we normally can't take for granted when talking about volumetrics. It's also possible to enable this with volumetric fog for higher-end use cases. And eventually, we will start to sketch out a plan of how to unify all the fog and volumetrics tech we have in the engine for a more seamless developer experience. Let's move over to my last topic, hair and fur. Targeting experimental in 5.4, we have added fine-grained groom streaming. This allows asynchronous loading of strands and binding data within the editor and during game. This brings a good speed up to loading grooms. Also experimental in 5.4 is a new auto LOD feature for grooms, which allows grooms to scale in complexity based on screen coverage without having to enter manual LOD information. While the quality varies compared to manually created LODs, it dramatically improves performance overall and is easy to use. Hair groom deformation can now be achieved through the deformer graph system, where groom attributes can be written out and guide data can be accessed within the mesh deformer asset for more fancy deformation like haircuts. And looking at the future, we want to bring the groom system to where we can use multiple grooms in a scene and have them perform well out of the box, something fit for game use cases. And we have future efforts along this line to rework some of the strand rasterization pipeline to achieve better performance. And with that, I'll hand it over to my colleague to talk about rendering architecture.
Thank you. Hi, everyone. My name is Mihnea, and I'm going to show you some of the exciting things the rendering architecture teams are working on. This is going to get a bit technical because we focus on performance and low-level systems, so I don't have pretty pixels to show you like Kevin did. I do, however, have some good news about shader compilation, PSOs, and a few other hot topics. First up, let's talk about what we're doing to reduce the impact of shader compilation on cook times. UE games have lots of materials which produce lots of shaders, and during cooking, they must all be compiled from graph form to HLSL and then some platform-specific code. A single material can be used in multiple ways, on static or skeletal meshes, with skylight or without, with light maps or dynamic lighting, and so on. We generate different HLSL for each combination of features, so this can lead to compiling lots and lots of shaders for each material. We're working on reducing the number of parameters which go into this system, which in turn will reduce the number of shader permutations we generate. For example, in UE 5.1, we've merged some vertex factories, which resulted in 20% fewer shaders being compiled overall. Static switches are another source of combinatorial explosion, so we're looking at ways to convert them to dynamic branches in cases where it wouldn't significantly impact GPU time. We also want to add tools to help artists understand how many permutations are produced for a material and why. For 5.4, we're improving shader deduplication. Many materials end up generating the same vertex or pixel shader code, but due to the way the system was structured, we were doing redundant compilation for each material. We're now storing individual shaders to DDC after performing pre-processing and dead code elimination, so duplicate shaders are only sent to the compiler once and simply retrieved from DDC when they're encountered again. This results in a 25% reduction in the number of shaders compiled in a full Fortnite cook. This is an active area of research and development, so expect more improvements to come in the near future. Next, it's time for everyone's least favorite subject, PSO stuttering. There have been lots of discussions around this subject, so I'm going to take a bit of time to explain what's going on. When we want to draw something, PC GPU drivers must compile the shaders used in that draw from the bytecode we produce during cooking, for example, Dixel or SPIR-V, to machine code, which the GPU can run. This can take a significant amount of time, tens or even hundreds of milliseconds per shader, and as I might have hinted earlier, games have lots of shaders. In older graphics APIs, such as the X11, this was all a bit magic, and the drivers did a lot of gymnastics to make sure the shaders were ready by the time the GPU needed them. When compilation was late, you saw a hitch, and there wasn't much the game could do to avoid that. Modern APIs, such as the X12, made this process explicit by having us package together all the shaders and render state used for the draw. This is called a pipeline state object. PSOs are great because, in theory, you can compile them way ahead of time instead of right before you want to draw something. For example, you can do it during loading or even while installing the game. So problem solved, no more hitches, right? Well, no. In practice, Unreal has a very flexible material system and rendering pipeline, which, as mentioned before, produces a lot of shaders. These get further multiplied by possible render states, such as vertex format, render targets formats, and so on, resulting in even more PSO permutations, possibly millions for all the materials in the game. Only a small fraction is used at runtime, but we don't know which fraction by looking at the material in isolation. Precompiling all these possible PSOs would take hours or even days, which is slightly longer than people are willing to wait for during a loading screen. For a very long time, our only solution was to record the PSOs which are encountered during playtests and precompiling those during startup in the shipping title. This manual PSO gathering was a work-intensive and error-prone process, which couldn't cover all use cases, especially in games with dynamic or user-generated content. Combine this imperfect coverage with the removal of driver magic, and you get longer and more frequent hitches and very angry gamers. The solution to this problem is our new PSO precaching system, in which meshes enumerate all their materials in post-load and kick off compilation requests. The mesh information plus the current renderer configuration allow us to greatly reduce the set of potential PSOs for a material. We still compile more than we actually need, but the overhead is manageable. For example, Fortnite renders about a third to a half of the PSOs it precompiles. This compilation is always performed, but drivers cache already seen PSOs to disks, so this only results in extra work the first few rounds of the game. Using Fortnite again as an example, this process adds about 15 seconds to the loading screen for the first time you join a match after installing the game. With a hot cache, the impact is negligible. We've launched this system as experimental in UE 5.2, and it's now production ready and on by default in 5.3. It's supported by the X12, and the mobile team is working on also enabling it for Vulkan and GLES in 5.4. Fortnite has switched to it since August and turned off the old manual cache, so we're no longer doing PSO gathering runs. And pre-caching gives us better results than the manual cache in Battle Royale and works in UFN2, where the old system was ineffective because we couldn't gather PSOs for materials made by creators. With a cold driver cache, over 90% of the PSOs are ready by the time they're needed, and there's ongoing work to improve this number. PSOs can still be late for a variety of reasons, and for those cases, the engine now offers two options controlled by the CVAR. The first is to skip drawing the object until the PSO is ready. Since most of the time this happens for objects which are streaming in, this option just makes it feel like it took a bit longer to load. In other words, it replaces hitching with popping, but in practice, players didn't feel like there's extra popping with this turned on. The second option is to draw the object to the default material until the PSO is ready. This prevents both hitching and popping, but it may look wrong, so please experiment to find the option which works best for your game. Finally, this system cannot help in extreme cases, such as teleporting to an entirely new location, or when changing graphics quality settings, or when assigning a new material from code. The game should try to mitigate the impact in these cases. For example, it can show a loading screen when changing graphics settings, or it can provide a list of possible materials in advance if it's doing runtime material assignment. Let's switch gears now and talk about what we're doing to enable the engine to render denser and larger worlds. Conceptually, Unreal has a game thread, a render thread, and an RHI thread. The game thread simulates the world. It adds or removes objects from the scene and updates their positions, animations, materials, attributes, and so on. The render thread processes the scene and builds lists of commands describing the work the GPU has to do to draw it. The RHI thread translates these command lists into graphics API calls for the current platform, like the X11, the X12, Qualcomm, etc. This split between render and RHI work is useful because API calls take time, and overlapping scene processing with command translation gives a significant performance boost. However, this model only uses three CPU cores, so it doesn't take advantage of modern hardware. Over time, some parts of the render thread were made to scale across all the cores using parallel iteration constructs, and we've added explicit parallel translation for simple command lists containing only mesh draw commands. Here's an insight trace illustrating the shortcomings of that model. For people who are unfamiliar with insights, each track here represents a thread with the RHI thread at the top, followed by the render thread, and 5 other worker threads processing jobs issued through Unreal's task graph system. The horizontal axis is, of course, time, and the colored boxes show what processing steps are performed on which thread. The steps are hierarchical. For example, this is the entire scene processing for one frame, which includes visibility determination, base path rendering, and render graph execution. I realize the step names and timing values are impossible to read, but don't worry about this at this point. The purpose of this is to show how much we're making use of additional CPU cores, and as you can see, it wasn't great. The render thread is obviously very busy. The RHI thread is fairly busy, but there's lots of idle time on the rest of the cores. This section in blue is RHI work doing explicit parallel translation of command lists. This section in yellow is the renderer computing view visibility with a parallel for loop, and this stuff is not rendering at all, just some pathfinding and decompression tasks which happen to run at this point. Over here, the workers aren't doing anything. To improve this situation, we've invested a lot of time and effort into restructuring both the render thread and RHI code into jobs. A lot of setup work, such as creating mesh draw commands and light primitive interactions, updating virtual textures, or updating the lumen scene, has been pushed to background tasks which can run in parallel with other scene processing. Most render graph passes also run as jobs, so graph execution uses all available cores. We've recently refactored init views as a multi-stage pipeline where each stage processes items in parallel. We're introducing a new API for render command pipes, which allows independent systems such as skeletal mesh updates and Niagara dynamic data generation to run simultaneously. Converting the renderer to this new paradigm will take time, but we're already seeing large performance improvements from this in the main branch, which will become 5.4. To exemplify, let's look into the visibility determination part of the frame. Parallel 4 was used to go wide in the frustum calling and view relevance phases, but this fork join model with serial sections leaves a lot of empty core time. After the rewrite, frustum calling tasks are launched much earlier. They feed into occlusion calling tasks, which then kick off view relevance tasks. This system has vastly better occupancy and scales with a number of processors. On machines with 8 cores, we're seeing improvements of up to 3 milliseconds, depending on force on scene complexity. Put into perspective, that's almost 20% of the frame time at 60 Hertz, and this is only one of the optimizations we're doing. The RHI thread was rarely a bottleneck before, but with systems such as Nanite pushing more commands through and with the previously mentioned optimizations reducing the render thread time, single-threaded command execution is starting to become a problem. Modern graphics APIs such as the X12 and Vulkan allow us to record multiple command lists in parallel, so the step which translates render commands to graphics API commands can take advantage of multiple cores. We've refactored the execution model so that non-immediate command lists, such as those created by parallel RDG passes, form a chain of translation jobs running on worker threads. One chain translates commands into a single API command list. When a chain exceeds a certain number of pending commands, a new chain is started which runs in parallel with the previous ones. This trade-off between how many jobs run in parallel versus how many platform contexts are active is still being tweaked and can be controlled via CVARs. Command lists which modify resources, for example, lock and unlock buffers, cannot be translated in parallel with others. When such a command list is encountered, the system waits for the active translation jobs to end, executes it, then resumes parallel translation. We're going to optimize the renderer to minimize the number of times this needs to happen. This is what the old execution model looks like. Meshed raw passes, such as the base pass and velocity rendering, explicitly created multiple command lists and marked them for parallel translation, but the rest of the frame was translated serially. This stuff over here is just a bunch of decompression tasks, not rendering work. With the new model, almost any command list submitted by the render graph is a candidate for parallel translation, so there's a lot more happening on worker threads. As I've mentioned earlier, command lists which mutate resources cannot be executed in parallel, so they run serially on the RHI thread. Fortunately, we don't have many of those, so they don't significantly affect core occupancy. I'll end this section with a comparison between the first screenshot I've shown you and the new trace taken at the beginning of September. This is CitySample running with we're running first with most of the optimizations here disabled, and then with everything turned on. So in other words, with the features available around when UE5 launched versus today. You can see that there's a lot less idle time on the worker threads now. More importantly, the render thread goes down from about 21 milliseconds to 11, and there's more to come. Moving on, let's look at things which are further down our roadmap. In UE5.3, we've promoted the neural network engine plugin from the research phase into experimental. This plugin provides an abstraction API on top of several inference engines, similar to how the RHI abstracts graphics APIs. We expect it will be used for many tasks which are not related to graphics in any way, but we've incorporated the NNE team in the rendering architecture group because inference needs to efficiently share execution resources with graphics workloads. Some of the inference engines run on the CPU and others on the GPU. The API is slightly different in each case because, of course, inputs are output and outputs are managed differently when they're system memory versus graphics resources. We've kept several use cases in mind when designing this API. The first is edit time processing, which will be promoted to beta in 5.4. In a way, this is the simplest case because it doesn't have too many constraints, especially in terms of processing time. Examples of this include automatic asset classification, content generation via something like stable diffusion, compression, feature extraction, and so on. The next two cases are runtime inference running on CPU or GPU, which can be used for controlling bot behavior, computing mesh deformation, denoising, etc. These will still be experimental in 5.4. The final application is evaluating neural networks inside materials, but the API for this is still being fleshed out. NNE has already been adopted for some internal applications, such as MetaHuman, where it's used to track facial landmarks and generate tongue animation based on audio, the ML Deformer plugin, which provides realistic cloth and muscle animation, and the Learning Agents framework, which provides reinforcement and imitation learning for NPCs. Other things on our roadmap, in no particular order, are bindless rendering. We've been working on this for a while, and we're hoping to have it available as beta on some platforms in 5.4. It should provide a performance boost because it eliminates the need to do descriptor management, which is particularly taxing in ray tracing. It also enables some new rendering techniques if shaders have access to all the loaded resources, but this explicit bindless mode is going to come later. Vulkan ray tracing. Unreal 5.3 has experimental support for Lumen hardware ray tracing in Vulkan. We're working towards bringing Vulkan ray tracing up to parity with the X12 in 5.4, including path tracer support, which should help licensees looking to use Unreal for offline rendering on Linux render farms. We're going to introduce a new API for creating and updating render resources. The current API is inconsistent between buffers and textures and requires at least one temporary copy of the initial data to exist in memory. The new API will allow us to remove these temporaries, and the wasted memory bandwidth will enable us to use the copy queue for uploads where appropriate, and will support direct storage. Another aspect we'll look at is frame pacing. The idea is simple in theory: predict the total frame length based on previous frames, then delay the start of the game thread work so that we can present the final image just in time for the next back buffer flip. This minimizes the input latency and simplifies the pipeline. In practice, this is a fairly large undertaking as it requires us to remove legacy and sometimes arbitrary sync points between the game thread, render thread, RHI, and GPU, which will uncover bugs and hidden assumptions in various subsystems. Finally, we're looking at ways to improve video memory management, especially when running the editor in the X12. The editor generally uses more memory than the game, and there are many cases where it's fighting for resources with other processes such as the browser, content creation applications, or even other instances of the editor or the game running at the same time. This is an active area of investigation for us, but it will take time for the systemic improvements necessary to be implemented and stabilized. And with that, thank you for listening, and thank you to everyone in our amazing rendering team who made this possible.
go. Hi, hello everybody. My name is Arjan Brussee. I'm head of product management on Unreal Engine, part of the dev team, and I'm going to talk to you about Unreal Engine 5 in its broadest terms. So there's going to be a lot of things I'm going to cover, so bear with me. It's going to be quite intense in terms of detail, and we'll follow up with some we don't have time for Q&A, but there will be a link to the roadmap that you can check out and look at more things that I'm talking about. So yeah, today I'm going to talk to you about where Unreal Engine 5 came from, right? Where the ideas came from and what we got to so far, right? We're going to touch on the just released 5.3 version, lift a bit of the curtain on the future releases that are coming, right? The future things that are in the pipeline, and you know, as a disclaimer, right? We generally want to under-promise and over-deliver. Right, and we're now going to show some of the things that are very much in development. So, you know, we don't have hard timelines, right? It's software development. We're doing some of the hardest things in the industry. So, you know, we'll update you on the feasibility and the timelines when we have better insights. But yeah, this is just like the forward-looking stuff as well. So yeah, the journey so far. You know, it all started with this first prototype we did back in 2020 called Lumen in the Land of Nanite, right? That really showed what was possible if you made like a next generation renderer, right? And, you know, we did this as a tech demo, you know, prior even to the release of UE5, right? And this showcased really this unbounded detail and complexity alongside with real-time GI that could do realistic dynamic lighting and dynamic worlds without baking. Then 1 year later, we went to a UE5 early access and showed off the capabilities with the latest demo and the early access release. So there, a lot of time was spent on workflows, right? Improving the workflows on world partition, one file per actor, data layers, right? Quixel workflows and further performance enhancements to kind of make all this detail kind of sing. Then at the end of 2021, we shipped the Matrix Awakens demo, right? It really showed the capabilities to render large-scale photorealistic cities and for the first time. But also includes high-end quality characters, high-end animation, post-processing, those kind of things. You know, this was built with a procedurally generated city, you know, built in Houdini, because we found, right, with its previous demos that we couldn't just hand place all this level of detail anymore, right? We needed smarter tools, better tools to create these large worlds. So then, right, part of this productization of all these features, we shipped it in Fortnite, right? And the big thing there was, you know, take a game that was basically UE4, right, in terms of assets, and kind of up-res it to UE5 and add kind of all these new features, add performance, right, running at 60 frames per second, but also having fallback options for previous gen platforms, right? And this was all shipped with 5.1. And then, right, last GDC, we took this procedural thing that we tested with really the Matrix demo, and we took that to the next level with Electric Dreams, right? And this was a system that we actually built inside the engine, so we could do much faster round tripping. We didn't have this import-export kind of flow of like going from the external DCC to internal, and you know, you could see what you were doing right in the viewport, etc. And that's alongside with this foliage sample that finally showed us some, you know, non-rocky and non-stone-based worlds in a demo. So yeah, you know, that's the journey. You all know that. But you know, if you look at all these things, then you know, you can see the pillars, right, of UE5. Right, these are all the areas we've been developing towards for UE5, and this is like the through line of the UE5 generation, right? So all these things have been released in some state of functionality, but some of them are also not done, right? These are things that we will keep on building on for future releases. And also based on the feedback we're getting from all you, right, that are using the technology. So, it is also a dynamic plan, right? So we will keep spinning up new areas where we see the need, right? But it's a good overview of all the areas. So yeah, let's go through some of the new things, right? Recent and new things. So I'd like to kind of go over like the aims, right? Like what we're aiming to do with these technologies, and then kind of go into 5.3 and then kind of go into future. Rendering, right? It's pretty straightforward, right? You want to be state-of-the-art rendering, at performance, right? 60 hertz on consoles is really the goal for this kind of level of fidelity, while also having fallback for older hardware and also other platforms that can't run this kind of level of geo. We also want to support high-end photorealism for all these other industries, right? Like Unreal is used everywhere, right? From film, VFX, architecture, product visualization, and such things. So for that, right, we have a lot of things in flight, and also with the reference path tracer support that the renderer has. 5.3. Bunch of improvements, some cool stuff. Nanite with programmable raster is now able to render masked and textures and WPO much faster, right? We have some quality improvements with normals and all that. Lumen gets a bunch of things, exciting. For instance, Lumen reflections can now be run on next to like baked lighting, so you don't have to run the entire Nanite Lumen pipeline if you don't want that or need that for your game. Orthographic rendering is exciting for many use cases. Volumetrics got a big update, right? We're looking at things like you can now transform cached fluid sims and instantiate them at different locations and time to get much more complex effects out of a single kind of cached sim. Also having that supported in path tracer, right, for like these offline things, and generally fluid sims and supporting sparse volume textures are now much more able to store volumetrics in lower memory and higher performance. Path tracer got a bunch of improvements, especially regarding initial support for substrate materials, so you can use those complex materials for like automotive type things and kind of render them with path tracer, as well as support for smoke, fire, clouds, like heterogeneous volumes there. While we're on substrate, still experimental in 5.3. We say like it should not be used for production yet, but we encourage testing it and giving us feedback, right? And UE5 includes many improvements there to performance and capability and stability, but again, right, it's not production ready yet. Yeah, so going forward, right, first thing, we really want to keep hammering performance, right? So performance at complex scenes, right? Like complex high-definition scenes on modern consoles, needs to hit 60, right? So we have work ahead of us to constantly kind of keep improving that, and while able to increase the fidelity. Really exciting is to see tessellation and displacement coming down the line. So that's very close, right? Probably 5.4. That you can start seeing that. A great way to add detail cheaply on simple base geometry by just entering displacement maps, right? Also we have nanite spline meshes almost ready, so that will be extruding static meshes, deforming along the shape of a spline, right? Useful for roads and such things, right? Very clear use cases, and substrate, right, to the next level. With substrate, right, like in many of our features, we really want to prove that also in our own games, right? And before we can call it production ready. So, we want to get substrate in Fortnite at some point and have it run without performance decrease, right? And then, call it kind of ready for general consumption. Last but not least, we have open development and R&D into foliage, right? Foliage right now at the fidelity levels that we'd like to see right, are not maybe fast enough, right? So, you know, we have to look at nanite, we have to look at lumen, we have to look at shadow solutions to really kind of get super detailed dense forests that are moving and all that and render those efficiently. It's a really hard problem. We don't have the solutions yet, so it's probably going to take a bit longer than certainly the next version, but it's an active R&D. So yeah, world building, right? So one of these other pillars, right? Big pillar in UE5, right? We want to really be able to create large worlds much more efficiently and effectively with UE, offering, you know, better workflows, workflow creation improvements with like 1 file per actor, world partition, data layers, level instances, such things, but also handle the streaming of content seamlessly, right? So we're using these technologies internally at all our projects alongside with many licensees. So it's not a early technology in that sense anymore because it's being used at scale really. But yeah, the goal is that we really want to aim for huge worlds, right? And we're saying like, well, you have to pick a number, 16 by 16 kilometers with millions of actors, right? And that means that to hit this kind of number of, you know, this extra order, multiple orders of magnitude, more objects, we need to work on performance across the board, right? It is things like adding objects to the physics world, lightweight instances, further streaming improvements, you know, all those things. So big things there. With world building in 5.3, you know, some exciting things. You know, first of all, nanite landscape meshes. So, you know, the landscape can now be rendered using nanite, which will greatly accelerate, you know, the rendering of shadows and the landscape in general. Right? You have large landscape import and export, so you can now use the world partition tooling to import really huge worlds into sections into your world. So that's that allows you know, that kind of stuff. You know, and for instance, like level streaming persistence as well is a plugin that we're doing that manages saving and restoring of specific properties of objects when levels are streamed in and out. So very useful. You know, going to the future, right? Many things, right, are still on the list. You know, and all these things we want to use to improve workflows, customization, quality, performance in general, right? And at any world scale and density. You know, some of the workflows are, you know, a new world partition hash that's coming that will allow for like 3D grids instead of like the 2D grid that we have now. And also make it easy to implement your own streaming solutions for your project, right? If you have some other kind of layout you want to go for. You know, workflow things like HLD and editor, right? You can now create and see those things in the editor. Great. You know, and I think I'm gonna have to look at the time as well, so I'm just not gonna read out all the items, so I'll skip over some of them. You know, we have this new system called 1 file per actor, right? We are seeing that with some of these super dense things, especially with procedural generated worlds, where you see like tens of thousands of objects, that's coming a bit of a bottleneck again. So we are now introducing 1 file many actors, so we can store the PCG content all created into single files to help with the file churn and the perforce and source control nastiness that happens otherwise. Yeah, you know, another kind of big thing is a next generation terrain system. So we have ambitious plan towards what we call like landscape 2.0. That's in really early development, right? That will take some time, right? But the idea is that we want to get the fidelity of landscapes to the same level as nanite is in normal placed objects. And there's a lot of research that needs to be done until that time. But we do have, you know, the ability to kind of extend our current landscape with like higher fidelity and potentially displacement coming in shortly with the nanite landscape. So hopefully that's kind of an interim step while we develop the new terrain system, the new landscape 2.0. And yeah, you know, all this stuff needs to work efficiently and scale to all these huge worlds. Let me take a sip. So yeah, the procedural content generation framework, right? We're really excited about that tool, right? It was showcased at GDC. It's really about this building large world pillar, right? So how can we build these worlds without having to hand place everything and relying on external tools and seeing it all in the viewport and iterate on these parameters. You know, it's also really interesting, and I keep repeating that, is it's a runtime system. It can run at runtime. It can even run, generate LODs at runtime. So you can have gameplay that affects the world and the placement of objects in the world by using this system. So that's a really powerful thing. We hope to see some cool things come out of that from licensees. You know, and obviously this can also be used for linear content creation, right? If you want to make movie sets or backgrounds for your product visualization and all that, these are kind of cool systems to use. So yeah, with 5.3 we have some initial work on like a hierarchical generation system that will distribute the graph execution at different grid sizes and share the results between LOD levels. So you can make things like high detail up close, low detail far away. We have external data processing, so you can now import Alembic point clouds, and that replaces our by now unsupported city sample rule processor that we shipped with the Matrix demo. So and now with the benefits of PCG on top of that importer, right? So it's a better way to interoperate with something like Houdini plus PCG, kind of a hybrid setup. You know, and a lot of usability things, right? People are using this stuff, giving us feedback, and we're improving that while we go. Future of this, right? It's a lot of cool things in flight. You know, what we want to do is work on the runtime hierarchical generation, so they can actually run inside the executable itself and generate all these LODs inside the game itself. We are aiming to get GPU compute and microscattering to work, so you can have like super fine detail up close, like running on the GPU completely. You know, allow for more graph execution, so you can kind of figure out like where at what point is the logic running, right? Is it running on certain threads? Is it running on CPU, GPU, or you know what's the difference between various platforms in terms of the detail level that you're aiming for? You know, many workflows. I think also a really interesting thing we're looking at is like we have this huge Quixel database of all these super complex assets, but what we want to do is make these assets like smart, so the Quixel assets have built-in smart rules, like using the PCG, so a tree knows that it can only grow on like a certain slope and not on a rock, and it will spawn bushes under the tree or maybe not in the shadow, right? So you have like all these kind of complex systems that you can now build and distribute with our Quixel library, and that will be distributed through Fab, right? So that will hopefully greatly accelerate building these worlds with this kind of content, right? So we're going to extend all our Quixel type things into like smart procedural systems. Yeah, you know, we are targeting beta ready for production at around 2024 with our continual development. So you know, a lot of work is ongoing. So good things. Pretty short term. Next topic, animation. You know, large goal we have is to push for this fully animation authoring pipeline, right? But bypassing the need for most content development to rely on these external DCCs. You know, this obviously helps for round tripping, right? You don't have to import, export, and you know, it will increase the iteration time. We also unlock the ability for people to animate in context, right? They can animate in the final pixels. They can animate, you know, while the lighting is on the character, while the character's in shadows, etc. So this is like a really new superpower for animators. So the animators that are embracing this see like huge increases in efficiency and all that. You know, it's also a flexible and extensible framework that you can be extending on with using Python and plugins, and hopefully we'll see marketplace plugins come in that really extend the tool set even further, right? And then, you know, last but not least, we want to make it easier to use, right? So right now, you know, it's maybe hard, but so we want to see more people become animators and effective in using these tools to create animations and create this kind of stuff. So yeah, 5.3, you know, big new thing is the skeletal editor. It allows you to create skeletons and edit the skin weights directly in the Unreal editor. You know, obviously, again, you don't need to go back to this external tool. It also means that you can easily add bones to any asset and put the weights on and deform static meshes without having to kind of do that workflow through an external tool. So again, that's a big improvement in time. Animation authoring inside the editor has gotten a large number of improvements, right? You have like things like smart baking of keyframes, a better curve editor with better usability and performance, showing motion blending while you're doing root motion preview, those kind of things. And you know, then, right, we're going on to control rig, you know, a huge amount of excitement about that, right? We're seeing now ways how to use external data that drives control rigs and that can procedurally create and modify the control rigs, right? But also kind of export control rig animations back out with FBX export support. ML Deformer now has a bunch of improvements where it's much easier to set up this training data while in the editor, so you don't need to go outside of the editor and see the results in the editor. And we've also released some of our training data from the GDC recently to do the really advanced muscle sims in external tools. So yeah, you know, future. Animation and engine is a huge push, right? So internally, we have most of our animators at Epic starting to use or already using these tools in Anger, right? So we're getting a lot of feedback from them, right? We're constantly iterating on the workflows and the feedback we're getting. So these tools are getting really much faster fast. 5.4 release, which we say like is a GDC release, GDC 24. Is going to see like a massive leap again in animation functionality across the board, right? On runtime and gameplay quality, we have been working on motion matching for a long time, right? And we now have that in active production with our internal projects where we combine it with layering and really get some really good results out of that. So that will now be more ready for people to use going forward. We also plan to ship example data sets and debugging tools alongside with this system, so it's more easy to kind of roll it out and see what's actually happening and why it's choosing certain animations or not. On our high performance bullet point, that is a kind of new unified animation pipeline that we're building. It's a longer lasting initiative where we aim to replace the animation graph logic by logic running on a rig VM. So it's going to be much faster, but it will also unify the control rig and the animation composition into a single framework. So with this system, we will run our next generation animation logic, and that will completely remove the need for animation blueprints and also remove the need, which is our goal, to have to nativize animation blueprints in C++ if you need to get the performance out when you're finally shipping the game. So no more nativization needed. Control rig, we're working on like making it much more modular, so it's more like a ability to kind of kit bash character parts with rigs together into new characters, and a ability to kind of deploy these control rigs as like modular parts that you can attach to your characters and all that. We also have the ability to kind of layer this, right? So you can layer control rigs on top of, like, for instance, incoming motion capture data or other animation data, and that can really help accelerate kind of general animation workflows, which is really new and exciting. Then, another thing is the deformer graph framework. That that allows you to add these real-time deformation systems on top of existing Unreal meshes and get to that level of fidelity. Sequencer, we a bunch of things in flight. Maybe a good thing to talk about is the ability to extend the existing behaviors to support like dynamic user-defined things coming into the sequence. So it allows you to make better interactive cinematic experiences instead of just the pre-baked things that don't have any relationship with what the game is actually doing at that very moment. So yeah, animation, a lot of things. So yeah, going forward, framework, right, for which we say is gameplay, AI, networking. That's that group doing all that, right, where the aims are to really democratize the creation of these framework systems and realize a great tool set for building these complex worlds, right? Complex AAA and large open world type things because they're pushing kind of the complexity furthest, right? We want to get there by improving performance, obviously a lot, but also helping improvements in workflow and scalability and efficiency. So with 5.3, we now have smart objects that support world partition, which is great. It works seamlessly with world position data layers, persistent levels, and it also has been improved to support nav mesh and physics to determine slot reachability and such things. We have a long requested blueprint merge tool, which is only available for data assets at the start, but we aim to have that ready for general data-only blueprints in general in the near future. Stage 3, we have now a debugger for it, and it has expanded kind of breakpoint and general debugging capabilities. Yeah, so future on framework, many things obviously in the pipe. You know, maybe some interesting things to talk about. You know, nav mesh and nav link to support huge open worlds and world partition even more in the flight. You know, instance actors and mass, right? That's a approach where we take improvements to the mass framework to convert mass entities to actors and vice versa at runtime to support a far greater number of objects, right? So objects close are maybe full-on actors and components, but it can you know, collapse into simpler mass entities when they're further away and vice versa. So it allows you to make crowds and large crowd sims and such things. Mover 2.0 has been in progress for a long time. It's getting close now. You know, it's a container from the many new movement modes, and we are spearheading it with a new physics-based network mover component. Then we have Iris, and Iris is our new replication system that's been in flight for some time. It's going to be much more efficient, especially on like dedicated servers, and it will move to the next stage of readiness when we have proven it in our internal projects shortly. The gameplay abilities framework, right, a fan favorite, right, is getting some good love where we're modularizing this over multiple plugins, which allows us to simplify these workflows for users, but also reduce the memory, reduce memory usage upfront. And then we have support for smart objects that also allow for player interactions and make these interactions actually client-side predicted, so you can use smart objects in multiplayer games. So that's also really exciting. Yeah, then moving on to simulation. So simulation, obviously a core part in making believable living worlds, right? And it's also core to building more photorealistic digital humans and VFX for both real-time and VFX and such use cases. And we're using machine learning approaches to ensure these technologies can be applied in real time, right? It's a kind of an optimization type approach. So with the simulation team, we've been pushing on all these areas for a long time, and it's really about features. It's about interop with other simulation systems like Claude, VFX, Niagara, gameplay, but as well as constantly aiming for performance, right? And we're going to use performance a lot in this slide. In 5.3. We have, improvements, big improvements in Niagara fluid dynamics, where you can now bake them, and general performance has been improved there. We have the new chaos panel cloth editor that allow you to make cloth and do better skin weight transfer algorithms, and also use our new XBBD constraint system to get like much more high fidelity cloth out of it, where you can make a trade-off in like speed and quality setup going forward for like even better looking simulations. And that panel cloth editor will also work together with ML deformer editor, so you can do it inside the editor and see the results of the training in live. So yeah, lastly with 5.3, general performance updates with destruction, rigid body, and scene query aspects of the chaos physics. So yeah, future, many things in flight. One of the interesting things is we're working on this replication model improvements to scale to like large scale network physics worlds, right? Where you're kind of simulating a more complex physically driven world and sync it to all the clients efficiently. Exciting to see that we now have a visual debugger in flight that is actually starting to work really well, and that helps you debug the state of the physics world and see where the performance are, see what things are sleeping or not. So that's in progress, because we're showing videos. It's actually working. We have a new vehicle system where it focuses on more like plug and play components of physics that you can add to any vehicle, right? So you can't only make simple vehicles, but you can make much more than just cars, for instance. That new character mover with the physics-driven motion is in flight and will be shown soon. Many ML learning improvements for cloth and flash that are in flight, and general performance. But especially things like when we scale to these next order of magnitudes, more detailed worlds, right? We start to find bottlenecks in many systems, including things like adding to physics world and such. So there's work there that's on the table. Then my own personal favorite is developer iteration, where we have a lot of efforts underway for quite some time now to help reduce the iteration times, right, and get that into a much better cycle. Obviously, right, this faster iterations mean more iterations in an hour means you can get to better quality in a given amount of time. So it's not just efficiency, but it's also quality that you'll reach with your experiences. So with 5.3, we now have multi-process cook in beta, which will help greatly to increase cook performance on single machines, right? On build farms or build servers or on your own machine, right? In Fortnite, we see 2-3 times performance increases in cooking using this. So it's well worth enabling that and seeing if it works for your use cases as well. Then we have virtual assets that are now production ready. If you haven't looked at it, that's really interesting for especially like distributed teams, where if you're using Perforce version control and a shared Unreal DCC, you can actually stream the metadata of the objects and the bulk data kind of separately, which will greatly increase sync speeds for people that don't need the source assets for all the things, right, that are in your depository. So yeah, beyond 5.3, a lot of further work on cooking, right? Like today we have what we call like iterative cooking, right? So every time, right, we have to refine all the things that are changing, and moving forward we are optimizing the cook process to also handle incremental changes to configs and code to avoid recooking the same data. Then we have target platform iteration workflow enhancements, where we can use like a new local DCC and a cooked output store and stream that to the console, for instance, via the network, which will greatly increase iteration speed instead of like copying files over to the platform. Async loading for editor and for cook processes will, across many threads, will greatly increase performance for editor load times of big worlds, but also play in editor and also the cook side of things. And then cooked editor, right? This is a request that we see a lot, especially since we've released UE Event that's using this kind of paradigm. This is kind of longer term, probably beyond 2024. It's modeled on the learnings of UE Event, but we have a lot of work to do to kind of make it engine ready capability. But yeah, there's interesting workflows where people, if they sync to a version of the editor that's built on the build farm, why not also sync the cooked assets so that they don't to locally cook things and convert things, and it will generally accelerate people's workflows that way. So yeah, then going on to the content pipeline, their aims there is that we want Unreal Engine not to be a walled garden, right? That's a huge thing. So our goal is to allow importing of data into UE and UE Event, but also export of data from UE Event, and all that through standard formats, right? So that's the direction we wanna take there. So to do some of these things, right, we have this new interchange framework that we are introducing in 5.3. That's kind of a new system that replaces the legacy import factories. And it allows, it's like a modular and customizable pipeline. So there you can now import things like GLTF and OBJ, as well as all texture formats are now running through that pipeline. And UE 5.3 also has this support for like importing and re-importing entire scenes using like USD scenes and such things. We have support for Material X in USD experimental. There's also improvements around materials and textures in general. You can do like multiple UV sets, but also have basic animation support to support more of these virtual production use cases that people are obviously using. And then we have like Tessellator to use for like a CAD type level importing. Beyond, we want to have FBX import run on interchange, so that's coming production ready shortly. We are looking at porting all our existing enterprise tools like Datasmith over to the interchange thing, so that it can benefit from the new capabilities. And then, we want to use Material X shaders and support those in Substrate, for instance, and those things. So yeah, modeling tools, right? Again, this is one of these things where we are building new tools and workflows for creators, designers, technical artists right into the editor. And it will help increase round-tripping times, as well as it's like an extendable and customizable tool chain that you can build up yourself for your own use cases. So with 5.3, a bunch of improvements, many things on like workflow, in UX with like new UI, a better selection first workflow, which has been a long-standing effect. We have like custom presets for tools as a new workflow. As a new tool itself, we have a new spline tool generator that allows you to make a new draw spline and revolve tool to kind of make more complex extruded things along a spline. And these tools will get a lot of enhancements going forward as well. And then we have like new display of UV maps and distortions and texel density type things, also kind of workflow things in the overall geometry pipeline. So yeah, going forward, a lot of further workflow improvements will constantly happen, right? We obviously have some catch up to do, but they're getting enhanced every day. Exciting to see is that we now have improved gizmos in the pipeline that will really help, make the interactions between UE type editing modes and external DCC tools editing modes more common. For instance, right, we're looking at a new arcball gizmo or indirect manipulation type gizmos. So this is really making the whole editing of objects a bit more modern compared to other tools. So yeah, then platform, right? So obviously Unreal runs on everything that has a GPU. And we want to allow you to make content that scales across all these platforms. With that, right, a lot of things in flight, a lot of things with 5.3 on mobile, right, where we have like runtime virtual texturing support, instance rendering improvements, fog volumes, all exciting. Nanite is now able to run on M2, so you can run it on your MacBook type class hardware, which is cool. We also have worked on better Xcode project setups and all that to make it more consistent with how Xcode workflows work in general. And that allows you to do also like the iOS simulator that's on the Apple Silicon to allow for faster dev iteration without having to run on the device and being able to kind of debug that easier as well. Then on XR, a bunch of improvements. So Nanite can now be configured as like a single pass when we select the instant stereo rendering option. So that's an improvement in speed. Lumen can now use view coherency between the two frames to kind of accelerate the lumen resolve, which is great. And then we have eye-tracked image generation with OpenXR, reducing the amount of total pixels shaded, right? The foveated VRS type stuff. So yeah, then going forward, right, we do want to allow or get the desktop deferred renderer on high-end mobile, right? That doesn't mean it's Nanite and Lumen, but it means that it's the desktop deferred renderer, right? So it's like PlayStation 4 level functionality in some ways. And we are also looking at ever improving the in-editor previews, so you can see the result of final pixels if you select a specific type of hardware and don't have to kind of look at it on the platforms itself all the times. Yeah, last but not least, next-gen audio system, right? That's another pillar of UE5. We've been expanding this feature set for some time now, and 5.3 is probably our biggest release since MetaSounds was launched in 5.3. So with 5.3, we now have MetaSound output watching, which is a way to enable Blueprint or C++ to watch for changes in the MetaSounds graph and to match gameplay and visuals together with what's happening in the MetaSounds. With the Builder API, you can now get faster iteration times where users can script and automate the creation of MetaSound assets kind of automatically. Audio bus riding means you can now link all these meta-sounds together and create new meta-sounds by linking them, but also kind of streamlining all that stuff together. Going into the future, we have audio insights, which will now enable creators to intuitively debug and profile CPU memory usage when you're optimizing your project and looking at sounds. General performance improvements there and workflow improvements to make like configurable nodes and such things. So yeah, a lot of work going on there. So yeah, that's kind of in a fast view all the things that are in flight. We have this roadmap site, right? We always called it the roadmap, but we only showed the kind of the upcoming release, which was just a month out or something. But now we are extending it to show like a future-looking roadmap. So I'm really excited to announce that this is now live, right? Since Monday, this is live. Scan the QR code, unrealengine.com/roadmap, and you see a lot of our future-facing stuff. Obviously, the next question is like, when are these things available? Because I want them now, and why do I have to wait for it, and all that. So, bear with us, right? This is a kind of a big mind shift change for us already. What we want to do is make this an evergreen thing. What we want to do is make it clear when things are ready for 5.4, and we want to commit to it in a certain release. we will move it to the 5.4 session much in advance, so you can see what's coming, right? We don't want to be a black box, right? We want to have open development. You can already look at our GitHub and see all the typing going on by all our smart people on all these new systems. But now, right, you can see the cards and the descriptions of these things. And you know, this is an interactive tool, so you can type feedback, right? So we're reading the feedback. It's going to be really useful for us to get this feedback on these future features to validate our approach. And that's it. Thank you so much.